Page. Welcome to BSDCan 2025. I'm glad you're all here. Word of warning. I believe there's a room mic, and you might be picked up. So if you go muttering under your breath, that might make it onto YouTube. So please make sure any mutterings are complimentary. Thank you. As you might know, our record attendance for BSDCan was 280 folks in 2015 and 2019, and we are not there this year. The good news is, wait a minute, why is this not advancing? Arg, I didn't even look. Fine, I'm starting this over. Computers were a mistake. Okay, the mic is hot. We had record attendance, but this year, I'm glad to say attendance is climbing every year since COVID. So we are building back. And if you add in, we've started tracking the plus ones and family members. So folks are bringing their families to do tourism stuff, and that's wonderful. So the annoying bit, nobody likes masks. We have immunocompromised attendees, though. And the BSD community needs an event that's safer for those folks. So I guess that's us. Speakers, if you're comfortable going without, please do. We also have people who are hard of hearing and would like to see your lips. So work with us, be respectful of other people. You might know, some folks will say that, well, you have times that masks are not needed, and you'll notice those because look at who's not there. That's when the immunocompromised people are stepping away. Oh, and TarSnap provided the masks up front, and they found some really good ones this year. So if you've got any family members here looking to meet up with the tourist group, because we have a QR code for you for the signal group, and okay. I've seen some students waving Palestinian flags as a protest. Please leave them alone. If the police get involved with you because you were teasing protesters, we can't help you. Enjoy Canada jail. Father and Son's Pub is our local if you're looking for a place to get drinks. Food. I want to apologize for confusion this morning. We should have notified people that we don't have snacks with the morning coffee, especially since the Dev Summit previously did. The university has raised their prices and money is tight. We should have communicated that better. Mea culpa. Absolutely. However, we do have catered lunches today and tomorrow, shawarma today, and Chef Rick tomorrow. What is Chef Rick feeding us? I'm sorry? Sandwiches and salads tomorrow, which will be better and different than what the university feeds us, and also less expensive. Also, you might notice during registration, we asked if there are any vegans, and so we could feed them properly. However, as we discovered last year, vegan food is pretty good when it's not pretending to be meat. So, if something is marked vegan, please let the vegans have dibs on that on your first pass through the line. Because last year, the first 50 people ate all the falafel. Oh, and same for gluten-free. Speaking of vegans, there were a fair number of you who registered. There's a QR code for a couple of you who are arranging dinners so you don't have to eat alone. And so, the boring stuff. BSD costs money. And unlike a lot of open source conferences, we pay travel for our speakers so we can bring them in from all over the world. We accepted papers from China, from Ghana, and there's no way these folks could afford to come here without support. But this is important, one, so you see the work they're doing, and two, this is the way that in 2030, 2040, we get Shanghai BSDCan and Ghana BSDCan. Not that I'm putting any expectations on you. So, a couple years ago, I came up with a way to solve this problem because the Canadian Mint has a gold bar that you can pick up. And right there, I had the master plan. BSDCan is funded for life. 3 seconds later, the plan hit a snag. So, we were forced to fall back on conventional funding means, that is to say, sponsors. Our platinum sponsor, Netflix. Gold sponsor, ARM. Other gold sponsor, Apple. Our silver sponsors, FreeBSD Foundation, Tarsnap. Our bronze sponsors, Clara, ISC, and NetBSD Foundation. Now, we would like more sponsors so we can invite more people from Far-Away-istan. But the problem is, since COVID, most sponsors they're just out of the habit. Things have kind of reset. And a lot of conferences didn't return. So if you work for a company, please think about us in your 2026 budget. And Dexter, where are you, Mr. If you give Michael Dexter a lead, he will be on it like a starving dog on meat. And Dexter is just one member of our operations team that put all of this together. The operations folks are separate from the papers. They handle the nuts and bolts. And I'm not going to name everyone because nobody wants to listen to all this babble from me. I am going to call out 2 people, though. Graham, are you in the room? Graham Percival. Or are you sitting at the front desk registering people like the steady, sturdy, unstoppable secretary to a bunch of scatterbrained nerds that you are? He is the one who glued the conference together. So I'd like each of you individually to walk out, since he hid from the accolades here, and thank him out there. I'm sure he'll love it. And Melissa Muth, are you in here? She is our university whisperer, and that's a black art. So, the ConCom, you will notice, they have these fancy rainbow lanyards, so they stand out. That will become important in a bit. We have an empty slot in the operations team. There's a vital person who doesn't have a backup. That would be Michael Dexter, our fundraiser. We really need someone who has a little bit of sense of detail orientation, who is good with invoicing systems and beating money out of the web interface. Because Dexter will get the agreement, and then they say, go to our web page to fill in the invoice. And it's infuriating. So, and this would also give you a chance to see how Dexter pries those doors open, which would make you invaluable to the next generation. So please, if you have any ability in this field, approach Dexter, see what you can work out. I'd love to have a couple. There he is, yeah, right there. Thank you. We have a harassment policy. We have a safety policy. It's on the website. Basically, in short, keep your hands to yourself. There is no space for sexism, racism, homophobia, transphobia. Tolerance is a mutual non-aggression pact. Or to make it real short, don't be a dick. If you have a problem, find a rainbow lanyard. We've had actual discussions and training on how to do this. Our first priority is the safety of attendees. If a fellow attendee says, that's not cool, knock it off, please do so. If a rainbow lanyard tells you to knock it off, you're on notice. If one of those folks escalates to me, I will boot you out of the conference. And depending on how bad it is, it may be a lifetime ban. BSDCan is about community, and community is about people. And people want to have an interesting time with interesting people from all over the world learning about interesting stuff. They do not want to know your joke about your least favorite minority group. Now the happy things. Hacker Lounge. Lobby of the residents at U90 building or 90U. People will be there. It's open 24 hours. You don't have to be staying in residence. There is a key card door, but show them your badge and they'll let you in. You don't have to be programming. That went too fast. That's where people hang out in the evening. Folks sometimes meet up for dinner. If it gets crowded, please put your mask on because, you know, we want the immunocompromised people to be able to meet for dinner, although many of them eat in their room. So experiment this year by popular demand. 11:30 is a quiet room. We get noisy and happy and excited. And did you hear about the new VM trick? Oh my God, it's amazing. 11:30, go in, check your email, quiet. Make sure your phone is on buzz. It is not a meeting room. I'll be stopping by to count how many people are actually using that to see if we do it next year. End of the con. Oh, we have bags for you. If you don't want your bag and this one single sponsor flyer that's in it, please return it to the registration desk and it'll be donated. At the reception at the end of the year, because, you know, we can't have a party, so we're having a reception at the end of the conference. We'll have a box. Return your lanyard if you don't want it. We'll use it next year. The high point of BSDCan is the closing session with the charity auction. We have auctioned off business cards. We have auctioned off servers. We have auctioned off Dan's shirt. You never know what's going to happen. Dan will be serving as auctioneer this year again. He is the founder of BSDCan, did it single-handedly for 19 years. And Dan, tell them what you'll be auctioning off. We have a mic.
I'll be auctioning off a used Trader Joe's paper bag.
$50.
Contained within that paper bag will be a, got to get this right, a Netgate APU2 BSDCan 2014 custom box. So this was my firewall for, I guess now 10 years. And every single byte that went through test stage or dev fresh ports went through this box. So it's still good, still works. We'll be auctioning that off. Thank you.
And proceeds, as tradition, to the Ottawa mission. If you want to see the Ottawa mission, walk down towards Ottawa. You really can't miss it. Closing reception, same as usual, Sen's house. We are interested afterwards in knowing how it was for you. We have it exclusively until 9 o'clock. So right after the auction, head down there. There better be plenty of food. Again, this year we've made sure vegetarian and vegan options. Again, please give them a moment to grab a mouthful before you devour all their veggies. Dan will be in control of the drinks tickets. You each get 2. Please don't auction off your drink tickets because, you know, I'm not going to name any names, but, you know, certain people could handle 9 or 10 of them, they think. And some daft person covered the reception fees for everyone who registered before 19 May. So it's included for most of you. So on to the talks. Did I miss something?
I noticed that there's a sponsor missing from your slide deck, Michael.
Yes, but we traditionally only list platinum, gold, silver, and bronze. So anyone else, they should have paid real money if they wanted to be on the slide deck.
The closing reception, Michael mentioned that if you registered before May 19th, your closing reception is already covered. You get to eat for free. And that is thanks to Tilted Windmill Press, AKA Michael. So, we'll buy his books so we can do it again next year.
I promise you the thought that drunk people buy more tech books never crossed my mind. So, we had a really delightful moment this morning because Kirk didn't read the schedule. Our keynote speaker is the brilliant Margot Seltzer. She wrote LFS, Berkeley DB, and this stack of awards and doctorates and a bunch of things that show she's really too good for the likes of us. And it was like CSRG Old Home Week here. So I'm going to shut up. Please welcome Margot.
Is the technology going to work dance? But I'll give Kirk a little more grief for not knowing I was here, since I actually talked to him. Okay, is there a power supply anywhere? There we go. Okay, I actually talked to him when I was asked to keynote, and it's like, hey, like, what should I talk about? I don't know. He gave me some suggestions about things I knew nothing about, which he probably figured I was comfortable talking about anyway. But he hadn't looked at the schedule, so he didn't know I was coming until I walked in. I, on the other hand, had looked at the schedule and know exactly when his talk is. But it's okay, because I'm going to walk out in the middle of it because I have a flight tonight. All right, I didn't know about the great reception. All right, let's see if the computer's actually going to work. No, you don't need my Slack window. Oh, yeah, we'll get to the plugging it in part. I didn't want to reveal all my email and things like that. Oh, it's looking good. All right, hold on. We got one more step.
Oh.
Presenter view. Patience. Oh my God, amazing. All right. Nothing can possibly go wrong now because the technology is working. So this is a little bit of a small, intimate crowd, so I will invite you to ask questions. If I don't, the talk is designed to leave plenty of time for that, or to leave questions at the end, so feel free to raise your hand. If I don't see you, wave it wildly. If I still don't see you, say something. First of all, I want to thank you for having me here. BSD was a huge part of my graduate school experience. I went to Berkeley. That's where I got to know Kirk and Eric. I married into the BSD family. I didn't realize that was part of my grad school plan, but it turns out it was. And then a lot of my early research when I was a young assistant professor was actually done in NetBSD. Now those youngins come along and they want to do stuff in Linux. I let them. But the people in my group who are doing security stuff still use OpenBSD. So thank you. I appreciate all the work you do, and this is a little bit of a homecoming for me. So this talk grew out of a workshop that I co-ran last year around April with some Google folks, so Dave Patterson and then David Bacon of Spanner fame and Karsten Binnig. And we brought together a bunch of hardware nerds and database nerds and threw them together for a week to figure out how on earth we're going to deal with the increasing scale of data that we're being overwhelmed with. And I learned a ton about it, but I spent a week and had to go to Germany to do it, and I'm going to try to bring you all up to speed on that in the next, like, 45-ish minutes. So, serious title there, maybe not so serious. The talk is really about memory, GPUs, and AI. Oh my, because this is what everyone's talking about. But don't worry, this is not a disguise for an AI talk. I will mention it on, like, maybe one slide. So huge thanks to Dave Patterson and Mark Hill, who are real computer architects. I am not. And I stole shamelessly from their slides with their permission. And then I'll get to a little bit of storytelling in a few slides. And helping me tell that story, one of my students, Shaurya Patel, went down a bit of a rabbit hole with me. And I will share with you that rabbit hole when we get there. So one of the things I teach my students is that when you write a research paper, you're really telling a story, right? So every paper is a story, because humans are like designed to listen to stories and narratives. Now, the fundamental story that we have in all sorts of different cultures is the fairy tale. So I literally make my students tell me what they're working on and what paper they're writing in the form of a fairy tale. So please join me in that little idiosyncrasy and let me tell you a story. So once upon a time, if you were building enterprise software, you built that enterprise software to run on big IBM machines. And then time passed, and then we learned to write enterprise software on mini computers. Who recognizes this? There should be some hands in the room. Thank you. OK. And we have some other ancient artifacts here. Then we learned to write them on workstations and PCs. It was a sad day when I had to remove Sun Microsystems from my OS course because nobody knew who they were anymore. Yeah, I was literally in the middle of a lecture. I said, and then this, and I realized that not a single student in the room knew who they were. That was really sad. Anyway, and then we ran them on like these high-end servers of lots of little workhorses. And then we run them on the cloud. And I'm pretty sure that somewhere you'll find enterprise software running on like IoT devices and earrings if you choose to wear them. So we've learned how to build enterprise software that runs on pretty much anything. So we're done, right? Nothing left to do? Well, maybe not. There's still a few problems we could work on. So there's always new features. Not all new features are good new features, but we try to do them anyway. One of my favorite mantras is just because you can do something doesn't mean you should do something. That often applies to new features. Security, I would tend to call it an impossible problem, but I think there are probably people here who work on it, so we'll call it just really, really hard. And then there's scalability problems. So I would claim that we've been doing new features for 60 years, and we know how to do that. Security, I think, is the Full Employment Act for security people, so we're not going to talk about that today. So instead, I'm going to talk about scalability. The other reason speakers don't wear masks is because we get dehydrated. All right, so we've had a couple, excuse me, we've had a couple of, frog, go away. Who invited the frog? Demon, yes, frog, no. Okay, so how do we deal with scalability? Hello. We all have lived through, maybe, that memory has actually gotten increasingly large, right? So when I was in grad school, if you had the 16 megabyte machine, you had the big memory machine. Yeah, things have grown. We also have seen the migration from hard disks to solid state, such that my own central IT department at the University of British Columbia, which has on the order of 60,000 students, does not use spinning media for anything. Everything is solid state. I was a little astonished. But there you have it. So we've made some real strides at dealing with scalability. So what comes next? And this is where I want to get into the rabbit hole that I went down. So the circles I hang out with seem to say this phrase all the time, like, applications are becoming increasingly memory intensive. And I have been hearing this for 5 or 10 years now. And so I thought, surely there's data that will support this statement, right? Because clearly it's true, isn't it? Well, let me just tell you that neither I, nor my dear friend Chatty, that would be ChatGPT, nor Gemini, nor my really smart graduate student who's been working in this area, nor Archive, nor Google Scholar, nor anybody could actually give me any real data that supports this claim. And yet, you will hear people saying it all the time. So I went down the rabbit hole. So here are some of the most often quotes that are used to justify this claim. So this first one is a paper from 2020 in Eurosys out of Google, and it's comparing two traces of real production workloads between 2011 and 2019. And they say that, the amount of data per cell, a cell is a cluster of machines, increased by a lot. And then in 2022, we get this statement that, the cost of DRAM is expected to rise to 1/3 of all the cost of our hardware. And then we get another quote that, in Azure, it's going to be 50%, or it is 50%. So I decided to try to find the data that justified these statements. And I'm going to share that with you. So here's the trace comparison. So on the left, we're basically showing you the fraction of the cell capacity on the y-axis and over time. And the big dark splotches here are the production workloads. Okay, so this is from Google. So those are the production workloads. And those really haven't changed much between 2011 and 2019. And so it doesn't take like a rocket scientist to see that the growth is entirely in the green. Okay? So what's the green? The green is the best effort tier. Well, what does best effort mean? It means I don't really want to pay for anything, but I would like to get my work done, so I'm not in the teeny tiny yellow tier. So the entire growth in we're using more memory are the people who don't want to pay anything. I'm not really sure this says anything about applications needing more memory. So I'm not going to blame the folks who wrote this paper, but I am going to blame all the people who cite it and use it as an excuse to say that memory demands have increased dramatically. Okay? So that was that rabbit hole. So, okay, let's look at the the cost of DRAM is going to reach 33%. So where does that come from? So that's a study of Meta's data centers. Or I'm sorry, Facebook, Meta, I don't know what to call them. They don't express time in years. They express time in what are called generations of their infrastructure. So the x-axis is a proxy for time called a generation that I could not map to any real dates. So here's how I did the mapping. Gen 1, Facebook opened its first data center that it owned and built in 2011. So before that, they had been leasing from data centers. So I'm going to assume, perhaps incorrectly, that that's their Gen 1. If I'm wrong and their Gen 1 is earlier, it's even worse for this paper. And then if you read the pros, they say, oh, and Gen 5 and 6 are future generations. OK, so what data do we really have here? What we really have is from 2011 until the paper was written in 2022, sorry. So we have 11 years. And the fraction of cost that DRAM comprises rose from 15% to 22% in 11 years. So it rose like 1% a year. Suddenly, that isn't painting a huge, compelling picture for me either. OK, well, let's look at the Microsoft paper. So Microsoft is writing a paper about the cost of DRAM. And they're quoting something that says 50% of the server cost in Azure, which, by the way, is Microsoft, is DRAM. Great. So clearly, there's some data to back that up. Now, this is actually a news article from something called nextplatform.com, quoting a guy who is, in fact, an engineer on the Azure cloud, but, oh, by the way, is also on the board of these consortiums who are promoting these standards for building bigger memory machines. I know I've gotten a little bit cynical as I've gotten older, but I'm just going to shut up there. By the way, somebody said something about YouTube. Are these being recorded? Yes. Good. As long as you weren't hoping on getting any of the hyperscalers to sponsor you, we should all be in fine shape. OK, so the last quote is actually from another paper. And this one, does this look familiar? Notice what the x-axis is labeled in? But notice we don't have Gen 1 to 6 now. We have an off by 1 error. We're Gen 0 to Gen 5. OK, but this is basically the same data that we saw before, which is that memory is increasing. But in fact, who knows how much it's really increasing? Because if you go from Gen 0 to Gen 3, we're back at this 15 to 21%. So we've only increased 6% in maybe 11 years. So I am totally unconvinced that, in general, applications are becoming more memory hungry. They might be, but I could not find data that actually convinces me of it. So what do I really believe? Oh, question, yes?
So I noticed these numbers are percentages of server costs.
Yes.
Do we have information about how prices per unit performance for the non-memory parts of the server have changed?
Yeah, so I tried to look at that. There's one paper, and I can't remember it off the top of my head. I'd have to look at my notes, that basically say that DRAM and CPU costs actually increased in parallel. But it's a great question, and if I were not too cheap to pay analyst reports, I could get their crystal ball predictions, because they never talk about the past. They usually only talk about the future. So I think there's a mystery here. Yeah? Oh, yeah.
So I'm old. I was building apps on PCs when they first came out. And so you're wrong. I think that when you pin this down to server applications and the sort of life cycle we've had around frameworks and thinner operating systems, thicker open source stacks, it's probably been stable-ish during that time frame. But like the timelines you're talking about, I think need to be anchored somewhere.
Absolutely. So you're 100% right. If we want to compare memory consumption today to when I was in grad school, because I'm old too, our high-end CPU server build machine, when we were doing the initial Berkeley DB development, was a 486 DX2. Okay, so yeah, absolutely. If you want to compare it to what we were doing 10, 20 years ago, you're absolutely right. We're total memory hogs. It amazes me when I look at how much junk is going on my machine, and it's consuming all my memory. But if we're looking at I think if we're looking over the last 10, 15 years, which is when people have been making this claim, I think the difference is not quite as dramatic. So great point, yeah.
The question I had was, are there data that are corrected for application density? Like, we run a lot more things on one server now than we used to.
So I'm glad you asked that question. I'm so glad you asked that question. I didn't set them up for it, though. Let's think for a moment about how hyperscalers make money, right? Hyperscalers make money by running your and your customers and lots of people's jobs on their clouds. So if I have a machine that costs X dollars, and I can pack more of your jobs on my X dollar machine, I make more money. So depending on just how cynical I want to be, I actually think a lot of this stems from exactly the point you're asking about, which is, if you're a hyperscaler, you want to pack as much stuff as possible into a single machine. And I'll come back to a little bit, some of the problems we have with that. And so this is the question I actually posed to my student yesterday. I'm like, is all this research about, we need more memory just because the hyperscalers want to make more money? And so are we really doing work in the service of like 4 people or 4 companies, maybe 8 if you want to go globally, as opposed to like the entire community and making the world better? And I don't know the answer, but I'm becoming a little cynical about it.
I have one more thought on this.
Yeah.
I think that the characteristics of how the users perceive the performance of their application and the effectiveness of paging systems and the I/O rates, there's a lot of relationships there. And so if people would tolerate I'm being swapped out poorly, they'll tolerate I'm being context switched better because CPUs have gotten faster, and so the app took a second or 2, it's fine. I think there's something there as well.
There's absolutely something in expectations, and the hyperscalers have to live with that, right? They've got to meet their SLOs.
Even enterprise running on their own data centers.
Yep, absolutely. Okay, so here's what I believe, right? I believe that, Chatty and all her friends, i.e. Gen AI and LLMs, are going to consume as much memory as we can possibly give them for the foreseeable future. I don't think this is forever, but it'll be for a while. And so this is just, it doesn't matter, right? All you need to know is the y-axis here is exponential, and the blue line is basically how big models are getting, and a model getting bigger just means you need more memory. So if 1 billion parameters was good yesterday, 1 trillion parameters is good today, and a quadrillion parameters is good tomorrow, and we're going to scale your memory needs by as much as you want. So those applications absolutely need as much memory as you can throw at them. Now, I'm a database person too, right? Data's not going away, right? We create more data every day. Pretty much something like every year we create more than we've created in all the years before that. And now we have Chatty and friends generating yet more data. There's a whole separate talk I could give about the dystopian future where all the data is generated by algorithms that we don't completely understand. So databases, right, or anything you use to store data, those are going to grow, and we know that they work way better if you can store all the data in memory. So yeah, people do care about having enough memory to store all their data. Data's growing, so yeah, we actually need bigger memory stuff. So I do believe in those things. I'm just a little more cynical than I was about the hype that applications are in general becoming more memory hungry. All right, so let's figure out what we're going to do about this memory problem. So in 2018, Hennessy and Patterson won the Turing Award, and they described that we are in this age of, it's the golden age for computer architects. And so, if you build big enterprise applications, you think, oh, great, does that mean we're finally going to have really scalable SMMPs? No, 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 that's not at all what they're talking about. What they were really talking about was the emergence of accelerators. And at the time, in 2018, they were talking about accelerators with a little a. So these are, things like digital signal processors, or encryption engines, or compression engines, or stuff like that. But fast forward 7 years later, and everybody's still really excited about accelerators, but they're really excited about accelerators that begin with a capital A, and we mean GPUs. They might be TPUs, whatever, but these are these massively parallel units that we want for ML, machine learning. All right, so what do we do with these big honking accelerators? What do we do with accelerators? What are our options? So here's kind of the landscape. On the x-axis here, we've got cost. And on the y-axis, we've got how applicable is something that you build. So at the bottom, it's very application specific. And the top, it's very general purpose. So if you talk to the computer architects and you say, what can you do for me in accelerators? They will give you pretty much two options, right? Option one is the upper left. Cheap accelerators that you can use for anything. And so this is things like computing CRCs, encryption, compression, stuff that is now built into many chips, right? It's integrated tightly into our actual CPUs. So that's one thing you can do. The other thing you can do is you can go really expensive and application specific, and you end up with things like GPUs. Anything here in the middle is hard, right? Because what you're saying is it's not cheap. There's a whole bunch of design cost, and it's relatively application specific. So there have been these enormous breakthroughs, right? Factors of 100 or 1,000 in doing things like SQL queries, very limited families of SQL queries, or doing genomic analysis. And these are amazing, right? You can build special purpose hardware that does this, but you're not going to sell it, online to anybody who comes along. You're going to have a couple of customers. So the middle area is really hard. So if we want to address, this need for sort of more memory and more scalability, what are our options? So I'm going to give us two strategies that we'll talk through in detail. So strategy one is, you know what? Everybody and their brother now has a GPU on their machine, right? And that's been true for a while, because remember when graphics processing units used to be designed for graphics? So you laugh, and I do too, but the architecture of the chips that are really good for graphics, fundamentally different than the GPUs that are being built today to do all this machine learning. So we still call them GPUs, because they are similar in spirit, but they're completely different breeds, right? These GPUs are designed for machine learning. All right, so if we're going to try to use those more generally, and I think this is a reasonable strategy, if you can make workloads that are GPU friendly, that would be a good thing. So let's actually look at what a GPU looks like. So to look what a GPU looks like, we're going to compare it to a CPU. So here's a big old fancy processor. And the key features are that it's multi-core. I'm showing 2 cores here. Maybe you have 4, 8. You probably don't have 5,000. But you have multiple cores. You have multi-threading on each core. And come on, fess up. How many of you, the first thing you do when you're performance tuning something, you turn off the multi-threading? Yeah, OK. And the other half that are too shy to raise their hands do it too. OK, so we've got multi-core. We've got multi-threading. We've got superscaler, so we can get multiple instructions going at once. And then we've got out-of-order execution, because who wants to wait on memory? Let's rearrange things and hope that we don't have a bug that destroys data. And then finally, because it turns out we like to deal with objects that are bigger than a native word size, we always build in some sort of fancy SIMD instruction that lets us operate on multiple data items at once. So that's, to a first approximation, what the processors that I know and love work like, and I'm guessing most of you know and love, and these are our friends. And now we're going to introduce the wily beast of the GPU. So the first thing we're going to do is we're going to say, so why do you do out-of-order execution? Well, you do out-of-order execution to get a little bit more parallelism and make things run faster. But that's not what we're going to do in GPUs. In GPUs, we're going all in on hyperthreading. So we're going to get rid of out-of-order execution. Think going from CISC to RISC, right? We're going to go for a really, really simple processor here. All right, so we've gotten rid of out-of-order execution. What do we do next? Next, we're going to look at the superscalar. Why do we do superscalar? Well, again, it's sort of a way of getting a little bit more parallelism. But we're going all in on threads. So let's get rid of the superscalar stuff. All right, and what we're left with is basically a really simple processing unit that we can hyperthread until we get lots and lots of those. And then we're going to put lots of those cores in a package, and we're going to build what we're calling a streaming multiprocessor. So, you know, if you squint really hard, it's what we thought maybe we could do back when we were trying to build big, large shared memory machines. And the difference is that they really didn't care so much here about the shared memory aspect. I mean, yeah, they share memory, but it's a whole different ballgame. So this is what your basic GPU looks like. Now, why is this interesting, and what has it done to our expectations about how the world changes? So let me show you data, like actually real data again. So now we have real years on the bottom, not generations. These actually map to points in time. And we've got essentially the past 55 years and the next 5 years that we're going to describe. This is logarithmic, so these are just orders of magnitude here. So the yellow and the black dots show you how many transistors we pack on chips. And I forget which is yellow and which is black. Yeah, black are CPUs and yellow are GPUs. But the higher order bit of the black and yellow is that we keep packing more transistors on chips, and it doesn't matter what you're building. We just keep packing more transistors on chips. Great. Now let's look at the solid lines here. So the blue is your single-threaded CPU performance. So if any of you were with me during the heyday of Moore's Law, right, 90s to 2000s, it was great. Every 18 months to 2 years, you bought a new machine. It was twice as fast. And it cost about the same amount of money. We'll come back to that in a minute. All right, so we got between 10 and 20x improvement over a decade. Cool. Another 10 years, still mostly getting the same improvement, maybe a little bit slower. We get about 10x in that decade. And then we run out of Moore's Law scalability, and things kind of level off, and single-threaded performance is no longer growing, and we start seeing a lot more multi-cores. OK, cool. So remember, the key thing to remember is we're getting about a 10x improvement every decade. If you look at the GPU line, we're getting 1,000x improvement in a decade. Now, you might say this isn't fair because they're getting it through multi-threading, right? They're highly parallel. But that's kind of the point. That's what they want to do. And here's the truly remarkable thing. So I didn't understand this fully until last summer when I heard a talk from one of the folks at NVIDIA. The biggest performance improvement they get in the GPUs is when they used smaller numbers for floating point computation. Now, at first blush, this might seem mind-baffling because they're doing all this, right? They're multiplying vectors of numbers. That's what all these machine learning algorithms are. It's just matrix multiply. But it turns out that you don't need the kind of precision that you get with 64-bit matrix multiply. And so they started going to like 32-bit or 16 or 8. And I swear to God, last summer, I didn't completely understand how they do it. They were talking about 1-bit representations to do these machine learning algorithms. Do not ask me to explain it. It felt kind of magical to me, but almost plausible. So it's a completely different way of scaling what we're doing. If they get it down to 1-bit, you might ask, are they going to be able to keep it up? And that's a great question. And I don't know the answer. But remember, the previous Moore's Law curve was double the performance every 2 years and keep cost flat. And that was what was really remarkable about it. The GPU market is growing very, very differently. So the data up until 2024 I got from Dave, and then I tried to update it for this year. And it turns out that NVIDIA has announced their next generation processor named the Rubin, after Vera Rubin. And the numbers in black are ones that I'm pretty sure about. The numbers in red were sort of my best guess that I could read out of the tea leaves about You know, they've started hyping it up. But the key thing to look at is that the bandwidth is 13 terabytes per second, which is amazing. The less amazing thing is how much memory you get, 288 gigabytes. So this is going to lead us to a real problem. How do you take advantage of terabytes of bandwidth when all you have are gigabytes of memory? And so what has happened is we've migrated from what I call the old memory, the old I/O bottleneck to the new I/O bottleneck. So again, if you're old like me and you hear I/O bottleneck, here's the picture you think of. DRAM fast, disk slow, boo. How do we move data around? That's where all the cool kids hang out because that's where the I/O bottleneck is, right? Others with me, this is what we spend our lives trying to optimize for. Yeah, okay. If you're more my kid's age, so you're a cool kid, like here's the new I/O bottleneck. Persistent disk drive and flash doesn't exist, only memory, and memory is slow. The new bottleneck is between the caches and memory. So everything in your life is going to fit on memory, and the problem is that the buses between memory and processors are really slow. Is that a hand? I can also repeat the question if you just want to yell.
No, I was just going to say that Netflix servers, most of the generations are constrained by exactly that memory controller bandwidth. We can't go any faster because we don't have any memory bandwidth left.
Thank you. OK, so that was also good. You gave me a chance to dribble water on myself, which made me really happy. OK, so why is this bandwidth, why can't we get the bandwidth to main memory? And so there's a couple reasons. One is, the controllers. But if you think about how things are built, right, you connect things with wires, right? And that is a fundamental physical limitation, right? So there's only so many wires you can run between like memory chips and CPUs and things like that. So if you were a hardware person and you were faced with this problem, here are the two techniques that you're going to use to figure out how to get around wires. And so this is called high bandwidth memory. So the first thing we're going to do is we're going to put memory chips on top of each other, right? Because then you don't have to run all these wires on the board. You're running them just vertically. And then the second thing we're going to do is we're going to actually mount them directly on the same substrate that we put the processor. So instead of having to use wires to connect them, we're still using wires, but they're basically VLSI wires through the substrate, not physical wires that you can actually pull out a magnifying glass and look at on the board. And so if you go back to the picture I showed you, right, these 8 stacks, that's what they're talking about, are these stacks of DRAM. Okay, and when they announce a new generation, what NVIDIA seems to do is here's the base generation, which will be called Rubin, and then they're already saying in 2027 there's going to be Rubin Ultra, and the Ultra is going to have 12 stacks. So you can expect to see the bandwidth increase by about 50%. I'm sorry, you'll see the data increase by about 50%, and we'll still have great bandwidth, but we still don't have a lot of data. All right, so the two things we're going to do is we're going to stack our DRAM, and then we're going to put it on the same substrate that we put the compute die. And most of the time, the compute die is your GPU. Well, 288, 400, that's still not a lot of gigabytes. So then what do is you hook a bunch of these things with their HBM up on the I/O bus, and now you've got sort of lots and lots of memory, more bandwidth than you know what to do with, and we still have a little bit of a bottleneck. All right, so now we have a whole bunch of high bandwidth memory. Well, we have some high bandwidth memory with great bandwidth, but not huge capacity. And the question for you is if you want to be able to leverage this, what do, right? And I think the question is, what things can you offload to GPUs? And you might say, nothing, they're terrible, they're awful. And that's my reaction too. If you want to do machine learning, they're great. But I think that if we want to be able to show the kinds of scalability that the hardware is offering us, we got to figure out how to use the hardware. So your good idea goes here. I am open to discussion and suggestions. But I think that if you want really, really fast memory, that's your only game in town. All right. So what if I can't do that, and I just want more memory? What else am I going to do? So here's strategy 2, which has been around with us from the beginning of time. What do you do when you need more memory? Well, you just buy more memory. But what does strategy 2 look like in this world? So the problem is that we've got, in theory, we've got compute to burn, but that compute needs more memory. And in these applications where we're talking databases, machine learning, that's absolutely true. Is it true in enterprise? I don't know. Is it true in your private data centers? I don't know. But what do you do if you really would like more memory, and you would like it a little bit without having to buy CPUs to go with it? So this is where lots and lots of hyperscaler attention is being focused. And the research community is like playing along, because the hyperscalers like having the universities look at problems they care about. And so there's this new standard, CXL. It stands for Compute Express Link. And the idea is that we're going to use it so that you can share memory theoretically across a data center. We'll get to the architecture that does that. Right? So the problem that the hyperscalers are trying to solve, and they are absolutely the folks pushing CXL, is that they have a problem that they call memory stranding. All right? So you're a data center provider, and you've got 2 different jobs here, one of which we will fondly call the memory pig, and one of which we will call the compute pig. So our memory pig doesn't use all the compute on a machine, but it's happy to consume all the memory, and it would like more, but it doesn't get more. And our CPU pig needs all the compute, but it doesn't actually operate on a lot of data. So you've got unused memory there and unused compute there, and that is bad for a hyperscaler because that's low utilization. And so what you'd like to be able to do is, as the game show says, phone a friend. Hey, you've got more memory. Want to lend it to me? How do we make that happen? All right. So CXL is actually three protocols in one, because if one is good, 3 is better. So CXL.io is basically fancy PCI. How do you set up interrupts? How do you configure things? CXL cache is super exciting. CXL cache says, if you're an accelerator that has like a few gigabytes of memory or a few hundred gigabytes of memory, you can treat that as a cache for the massive memory pool out there. And the hardware will do all the cache coherence for you. Wouldn't that be lovely? Guess which protocol is not embodied yet in any device you can buy on the market? Cache. Coming real soon now to a chip near you. And then the third one is memory. And this is, so does anybody remember the distributed shared memory movement of the 1990s? Yeah, so love Kai Lee, think he's fantastic. He invented it. It seemed like a wonderful idea. And the idea was you have a network of machines, and imagine that you could use all their memory as a big distributed pool, and it would all happen transparently. And we built systems like that in software. And those of you who weren't there, what happens when you do that and your memory is sitting on a different machine? Just take a guess. It's really slow, right? Networks, not so fast. OK, so distributed shared memory did not take off, but there were hundreds and hundreds of papers about it. You could go to entire conferences where 1/3 of the conference was distributed shared memory. CXL is hardware-based distributed shared memory. And so the key thing there is you can use loads and stores to get data off somebody else's node. Right? Kind of a cool idea and implemented in hardware. All right. So if you go and look at all the fancy stuff, they'll tell you about 3 use cases. I'm going to focus on the rightmost one, which is the solution to the buy more memory problem. Right? How do I use this, the memory portion of CXL, to actually grow my system? Here's the way to think about it. It's another layer in the memory hierarchy. Right? So you've got really, really fast cache. You've got local DRAM, direct attached. And then you've got remote DRAM. And this time, instead of going over like Ethernet, which is what we were doing in the 90s, you're going over your high-speed data center interconnect. OK, and then you get to SSD, and clearly CXL should be faster than that. All right, so how do we expand applications memory? So as I've been saying, borrow memory from a friend. So that makes sense. The other thing you could do is you can just have memory nodes, right? Just vast banks of memory, CXL controller in front of them, and now this compute node has, oh dear, it looks like a NUMA architecture. I have some DRAM that's really fast, and then I have some other DRAM that's not quite as fast. So all that work we did on NUMA, or maybe we didn't, maybe we should, I don't know. All right, so that's another architecture. Now maybe you just want big memory pools that you mix and match among machines. You can do that too, so you can do memory pooling. And let's imagine that that's still not big enough. Then what you can do is you can get a switch that talks CXL, and now you can essentially turn your entire data center into one big memory pool, right? And you can attach different kinds of memory here, right? You could attach DRAM. One of the really interesting use cases is you can also attach brand new shiny DRAM that's really fast and older DRAM that you would normally throw away. But if you're already dealing with NUMA and you've got different latency memory, maybe you can keep that old memory and reuse it. So there's a whole line of work. Perhaps some of the most exciting to me in the CXL space is how we actually make our data centers greener by reusing memory for longer. So that's kind of cool. Or wait, maybe we could put persistent memory. And then you'd have that as another tier. Oh, wait, no, we can't do that because you can't buy persistent memory anymore. Oh, bummer. OK, so just a little bit of a poll here. How many people were really excited about Optane and the thought that you could finally have technology that was as fast as DRAM and persistent? Like, I totally bought into it. I wanted this so badly. We were very disappointed. But here's the weird lining to the really ugly rain cloud. So I spent a bunch of time being very excited about persistent memory and trying to figure out how to make it work. And then I had this realization, which is like, let's imagine we really kept our data in persistent memory. What happens when your machine burns up? Now, admittedly, this shouldn't happen very often. But as somebody whose entire data center was flooded by the sprinkler system, bad things do happen. And if you have important data, you're not supposed to lose it. So I started wondering, like, wait a minute. If we're really, the beauty of disk drives and SSD, like, you can unplug them and you can move them, right? DIMMs, it's a little tougher to do that. So I started asking people, like, so if I really care about this data, I probably have to replicate it. And if I have to replicate it, like, how much benefit is it that I'm running at close to memory speed? Like, is that really a win? And so I kept giving these talks where I said, what is the killer app that is going to make this work? And that's exactly the response I got. So loved the concept of persistent memory, like thought it was just fabulous. But even before they canceled it, I started becoming worried that there wasn't a way to use it. And if anybody finds this interesting, talk to me at the break about the Konami bubble machine. And I'll tell you about how history repeats itself. OK, so quick digression there. Oh, wait, there's one more step we can go from 2B, which is we can have lots and lots of CXL switches. This is where you get your entire data center as a big memory pool. And then they give, this is so fancy, they call it fabric-attached memory. But it's just like we know how to build hierarchy, and that's all they're doing. All right, so that's the buy more memory approach. And so the question is, are there use cases for that in the things you're deploying? And I think maybe there are. There are CXL parts coming on the market now. But I think what it really means is we really do have to think about NUMA either again or finally, depending on where you ended up in that. All right, I am going to wrap it up there. Quick thank you to the NSERC, who's the Canadian National Funding Agency, who had the good sense to convince me to come to Canada 7 years ago. I'm a happy Canadian citizen now, perhaps happier this year than I was even last year. And thank you to UBC, who has been a great home until they made me a department head. Not happy about that. But mostly, I am grateful for the amazing students I have, many of whom are deep systems hackers, many of whom do other things too. I've never met a research problem I didn't like. Short attention span, research problem I didn't like, you pick. But they make everything work, and they get all the credit. And on the slide, I just want to pause for a moment and leave you with an observation and a plea. So I go to a lot of conferences. I've been doing this for a really big number of years. And walking in today was one of the less comfortable ones I walked into, because I looked around. There weren't very many people who looked anything like me. I understand it's hard, but not shown on this slide are my 2 awesome graduates from a year ago who were the best undergraduate kernel hackers I have ever had in 30 years as an academic. They were stunning, and they were both women, and they're rock stars. And they're now working at various companies doing great things. So we know they exist. They are existence proofs. Anyway, there's a lot of people who don't look like us that aren't in this room. So that's my observation and my plea. And this gets back to the opening, right? Attendance still isn't where it was. If every single person in this room makes it a conscious effort to bring a friend next year who doesn't look like you in some dimension, I don't care what the dimension is. I have a colleague with blue hair. I could bring her, right? Bring somebody who doesn't look like you, and we will all be better for it. So that's my plea, and I don't know what our time is. I'm happy to take questions.
Am I on? Okay. I'm going to bring in the AI specter.
Cool.
And I've actually given talks somewhat similar to yours, not quite as focused at the low-level memory architecture, but more at this evolution of computing. And so I was at the beginning of the PC era where PCs replaced mainframes. Mainframes had lots of peripheral circuitry around I/O and things like that, so that the CPU, which was not very fast, could do its tiny best and channel along. Punch cards have entered the chat. And then, my whole career has been defined by that sort of microprocessor von Neumann architecture and the memory bandwidths, and like Xbox, we sat down and the problems we had were all about memory bandwidth, right? And I look also at this era that has defined my entire career around what people call all the time digital transformation. And as someone living on the front of that, I always sneered at that term. And now I'm waking up to the fact that we're at the end of an S-curve where there is no segment of our lives that has not been digitized in some way. We are all increasingly, unfortunately, gig workers to some software system that determines what we do, even teaching. And Moore's Law has been dead for quite a while, right? It was never a law, it was always a goal at Intel. And so that sort of compute cycle has changed. And for better or for worse, we can look at the AI space and we know that half of the time, at least, they're hallucinating complete junk. But the other half of the time, they're doing some really interesting things. And it challenges what we think about in terms of what software development means, because the lifetime of a program used to be one of the most interesting attributes of a thing. If this is a long-learning service, we're going to have it run all the time, it's going to be maintained by engineers, we can do all the engineering practices. If I can tell an LLM to generate the program I need, and then next week I tell it again, it generates something functionally equivalent to that, and it's running in some cloudy pile of GPUs or TPUs or whatever, everything changes. Like how we think about software development and how the energy goes in. And I also want to draw attention to like industry trends go where the money is. And the general purpose computing that was possible because of microprocessors drowned out anything you could do with much more custom design and carefully like that. And same thing for batteries and same thing for smaller, lower power consumption. Apple won on the AM circuitry because they focused on heat dissipation and power rather than raw throughput. And turns out those ended up being the bottlenecks down the road. And so I think your first strategy is actually the right one, but not how can we, doing normal von Neumann type architecture processing, go off and start using memory better, but more how can we realize that this is the next generation of computing and our CPUs will be relegated to the I/O processors of our mainframes. So it's not really a question, it's a statement, but I'd like to hear your thoughts on it.
Yes, this is our existential threat. Opportunity, great, yes. Point taken. So, wow, there are so many answers I have for this in so many dimensions. So I will do a random assortment, and then you just cut me off when I run out of random things or when you get bored, right? So, I got invited in the fall of 2023 to do a panel on Gen AI. And I was like, I don't do Gen AI. I don't do AI. I do a teeny little bit of ML. No, we really want you on the panel. We went back and forth. I agreed to do the panel, and I see their first description, and they say, 4 experts in Gen AI, ... I'm like, no, you can't say that. Then they changed it to, get this, 4 theoreticians. And I'm like, no, you can't say that either. We finally ended up with 4 computer scientists. So the thing that was remarkable about this is that I found myself on this panel, which I now fondly refer to as Margot and the Fanboys. And it was the first time in my career where people who I knew, respected, who I thought were really smart, had gone completely off the deep end on a technology. And then, fast forward a couple years, I find that I am actually married to somebody I know, like, respect, think is really, really smart, who's gone pretty far off the deep end on Gen AI. So I get pushed on this a lot. And there are a couple things I come back to. So one is code is not correctness. And there is nothing in the Gen AI stack that is designed to guarantee correctness. And we've come to expect certain levels of correctness in our systems. So I think that, if I build a GUI, which is something I've never built in my entire life, I have no interest in learning how to do it, but I am absolutely happy to ask Claude to help me do that. And if there's a bug in it, maybe I don't care. If it's my bank software, I think I care more. So I think, the position I tried to take in 2023 is that, these tools are tools, and they're going to be part of a much larger system. And we've seen that, right? They call it an LLM, but now what you actually have is like, ooh, this is a math problem. I'm going to ship it off to somebody who actually understands math, right? And so they're starting to build a system around this. We are system people, and so far, the tools haven't gotten anywhere close to really understanding how to do what I call system-level stuff. Will they or won't they? We can talk that for hours over beers anytime. I don't think it's obvious that we'll be there soon. Will we get there? I don't know. One of my former colleagues is at Sydney, and he's now he was one of our sleepy cats who built the Berkeley DB system. He was also then a wired tiger who built the system that underlies MongoDB. And he's now playing with Gen AI tools to figure out how much of the work can they do in trying to build a robust data storage system, right? One of the pieces of software that we like to describe as, when it fails, your customers have not only the desire to hunt you down, but the time, because you've lost their data. So I actually think there's a huge amount of work to figuring out how to use these tools to do the kinds of things, like, the value we bring is not the lines of code we write, right? It's understanding how systems work and how to get things right. And I would like to believe that getting things that work correctly is actually important. I could be proven wrong. I don't know that I want to live in that world, but we'll see. So that's part of the answer. The other part of the answer is, in my faculty meetings, every time we talk about hiring, and you might imagine that all the AI and ML faculty are like, we need to hire an AI and ML. Even though we have 50 people, we need 50 more. And there's a wonderful paper, I want to say it's from like 2010, and it's called, it's from Google, and it's called Technical Debt in Machine Learning. And see figure 1. And figure 1 is like a full, width of a page, and there's this teeny box in the middle that says machine learning. And everything else around it is what we do. It's system stuff. There's another box that says feature engineering. We'll give them that one too. So I think that there's still the need for stacks. I think it's an open question how well these tools can help us. So on the top of my to-do list in my copious free time is some of the machine learning research I do. We have this big pile of C++ code that needs to be refactored, and it needs to be integrated with a bunch of new features. And I want to see if Claude can help me. So this is like my project that I am dying to find time to do. And if it works, I'll come back and report back. So long, windy answer, which is I haven't a clue, but I have some random thoughts. Yeah?
When you were talking about PC evolution in the 90s, you mentioned that should I come to you?
I'll run. This is how you get your exercise.
When you were talking about PC evolution in the 90s, you mentioned sort of every 2 years you'd pay the same price for your newer PC, and you said you'd come back to that point. And it was really notable on the graph of, I think there were generations of NVIDIA architectures, how the price was increasing. Could you say more about that?
Yeah, so I don't have a great explanation, but you're right. I didn't come back to it explicitly, but when you look at the NVIDIA, right, we get a new generation every 2 years, great. They're not doubling in speed. They're changing in all sorts of weird dimensions. And NVIDIA charges us more for them. How is that fair? So I think this is much more of a technical, an economic argument than a technical one, right? Which is that a bunch of companies did not see what was alluded to in the last question, the transition from CPU-centered computing to GPU-centered computing. And NVIDIA did. And they went all in. And other people didn't, right? So who would have thought that even 5 years ago, if it was the middle of the pandemic, 7 years ago, if I had come here and said, Intel, 10 years from now, they're going to be in a world of hurt, right? You would have laughed at me, right? Who would have thought that? But here we are, and NVIDIA is, the golden girl. So I think it's more about they can charge us that. And in the 90s, when we started seeing, right, there was actually a lot of competition in the chip market, right? In the 80s, we had the Motorola's and the Intels and all this other stuff, and then it became a monoculture. And by the time the monoculture really got established, the curve had started slowing down. So I think it's more about economics, and I won't even begin to try to talk about that. I faked it with the Gen AI, but economics is too far. But that's my guess. Any other questions? Yeah. I'm making him do as much running as possible, so then I'll come back down to the front.
Thanks for the presentation. I was just wondering, doesn't the memory sharing system over the fabric stuff, that CXL, doesn't that pose huge security questions about how data is shared across the fabric? I know you said you didn't talk about, you don't want to talk about security, but.
Super great question. So I'm not the security expert. One of my colleagues, her main focus is side channel attacks. And so she has been looking at the CXL protocol and actually trying to figure out if there are vulnerabilities to side channel attacks. Shockingly, she believes there are and that they've found one. It turns out it's really, really hard to get the right data. If anybody happens to have one of these really expensive $500,000 PCI analyzers, we would love to borrow it. But yes. And it's not, you can always encrypt the data when you're moving it around, but observability of the pattern is absolutely, possibly a side channel. We'll know more over the next couple years as people really try to figure it out. But yeah, you're 100% correct. And I think that's really true anywhere, right? So we can watch data travel across the internet and have side channel attacks there too, even if it's all encrypted.
I'm just going to pile onto that. Every CPU optimization you talked about in the first ones has resulted in nasty, awful security problems.
Yep. Absolutely. I have theories about how we're going to solve that, but they're a little crazy. So again, the coffee break. And then there's a question in the front.
I was just wondering if you could speak a little bit more to the challenges of NUMA with like CXL. Does that differ a lot from traditional like commodity NUMA systems? Are there additional dimensions aside from just access latency that cause problems? Or
So I think, at the end of the day, yes, you've got memory with different latency. So in that sense, it's exactly the same. I think the way it's different is scale, in that we can now have NUMA access and latency changes across a whole data center instead of within a single system. So I think that's a little different. And the other piece of it is that, and you run into this in a single system, but I think it just becomes bigger and more complicated, is when do I keep accessing the data remotely, and when do I actually try to move it between tiers? And so I think it's the same kind of problems. I just think we've made it bigger and maybe more complicated, but maybe not fundamentally different.
I was just wondering about that. I mean, yeah, is like variance of access latency more of a problem? Or is it going to be pretty consistent?
Yeah,
I have no
so
real intuition.
I don't feel like I have enough data on the top of my head to answer that definitively. Clearly the number of switches you go through is going to add latency, right? And so as soon as you're talking about like a fabric, then you clearly are going to have different tiers, multiple tiers within this thing, and more of them than I think you do in a conventional system.
So I'm thinking we'll know whether or not CXL is going to be a win when VMware implements it.
You mean
'cause
Broadcom?
Well, in the VMware product family, yes. I figure if they're implementing it, that means it's here to stay for a while. Of course, that leads me to my first concern is how long is it before Palo Alto releases a CXL firewall? The thought of which just sickens me, but there you go. I'm sure it'll happen. It seems to me that would be actually one of the most easy wins for it. Is like I'm not a hyperscaler. I'm maybe a mini scaler, if you will, and like we migrate VMs approximately one every 2 to 3 seconds, all day, every day, to rebalance loads. And if CXL allows the memory of that running process to be accessed remotely, hot migration just becomes a lot easier. They don't have to do all the state tracking and snapshotting of memory and all that stuff. You can just access the running space directly over the wire.
That's a cool idea. So I haven't heard anybody working on it, but that's actually a great application of it. I would love to see. That's a great idea.
Seemed obvious to me.
You think about different problems than I do. Yeah, no, I love it. That's great. I can admit a new PhD student now.
Yeah, I just on hearing that, like, you do copy art, right, with it? But the other thing that occurred to me for CXL was I used to work at Pandora, and we'd have tiers of media servers for doing our serving. And the first tier was everything out of RAM on the local machine. And the second tier, we had very expensive specialized PCI Express cards that had a bunch of DRAM on them and looked like RAM disks to the machine. And CXL would be like the next generation of that technology. So
Yeah, instead of making them RAM disks, they're just
right,
more memory.
anyone doing streaming media would find those for like the high use pieces of data.
That's great.
Yeah.
Okay, so we're going to start our little CXL company after meet us in the lobby. All right, looks like maybe we're running out of questions or people need more coffee. Yep, all right.
BSDCan, so I'm glad to be here, both at BSDCan and as a presenter, so it's absolutely stunning. And I came here to tell you why and how we are migrating many of our servers and our customer servers from Linux to the BSDs, and how the things are going. But to get into this, I have to start with my own personal story. So it will be something stretched between technology and personal life. So the first thing I should be doing is introducing myself. I am Stefano Marinelli, and I solve problems. I'm the founder and barista of the BSD Cafe. The BSD Cafe is a community of BSD enthusiasts and people just passionate about technology, about open source operating systems, just curious, and that want to get more into the BSD systems. And the target of the community is just to create a relaxed and peaceful, inclusive, and open environment in which everyone will just feel relaxed and ready to ask any kind of question, or just look at what others are saying or writing for their own personal growth and the community growth by itself. I work in my own company called Prodotto in Rete. It's, of course, an Italian word, but more about this later. All I can say now is that the company is just a container of ideas and solutions. But yeah, more about this later. I'm passionate about technology. I'm passionate about computing. I used to say that I was born with a keyboard under my arm, and it was quite straightforward to make my passion my profession. And I can say I'm lucky enough to wake up every morning with a smile, say, oh, great, I'm going to do some funny things today. I'm not sure what I'm going to discover today, but it will be great. So at 45 years old, it's quite nice. How did I get into the open source operating systems and the BSDs? Well, I started in 1996, before even turning 17. I was reading about those open source operating systems on Fidonet, you know, the BBS, Time, all those old modems. But I couldn't believe that something, a free operating system family, free operating systems, how could they work? I mean, nobody's getting money from them. I was too young to understand, to fully understand. But I found an advertising on a magazine, and they were just saying, you can buy this CD set, we will ship them to your address. It was quite cheap, to be honest, considering it was coming from abroad. And you don't need to download anything. So I said, why not? Let's try this family of operating systems, the open source operating systems. And when they arrived, I found those CDs contain many Linux distributions. So I started to install them inside my computer. It wasn't a powerful computer. Of course, I was a teenager, I was a student, so I couldn't afford to buy a computer just for those tests. So I just created a small partition beside my Windows partition. I started playing with those distributions. And it was love at first shell. I mean, I found, when I saw that cursor blinking, I didn't see a cursor blinking. I saw a blank canvas, a powerful tool that was going over all those, you know, graphic GUIs with checkboxes. I just felt I could pipe comments together and realize everything I wanted to. Like, you know, the Lego bricks. You can just combine, mix and match, and create everything you want to. So that was beautiful, but my hard disk space was quite limited. So I had to consider to use Linux just for some tests and not for, you know, real world, real life use. So I kept it in a small partition and used to play with it from time to time. But everything changes 1 year later when I bought a, you know, faster, bigger computer, and I could use Linux and Windows side by side. And I found out that I could do anything I needed to with that Linux operating system. So open source, free, because I did not pay for the operating system, but just for the CDs. And it was, you know, I felt the freedom of using those tools. So I immediately understood the power of the open source world, of the open source operating systems. That led to give Windows just a small partition for gaming. At those times, Linux wasn't great for gaming. And in 1998, I started my university studies in Bologna, Italy, computer sciences, of course. And I found out that the computer science courses in Bologna were quite open source oriented. So many of my colleagues, students, weren't aware of the open source operating systems, Linux operating systems. So it was beautiful because I was one of them who could immediately get into the spirit of the university labs, of the university team. And I eventually became one of the administrators of the university labs. And they were totally based on Linux solutions. So my studies continued to go on. And in the year 2000, so 25 years ago, I started attending some courses by Professor Ozar Baboglu. And Professor Baboglu never explicitly pushed towards the BSDs, but you know, with students, he's one of those who created the BSD operating system. What's this BSD operating system? I know Linux. Linux is open source operating system. What's BSD? So I started studying about those BSD operating systems. But you know, I couldn't access a broadband connection at those times. So I just had to study online documentation, and my computer wasn't great to read the documentation. So I had to postpone the real, you know, hands-on on BSD operating system until 2002, as I got a new computer. I got a broadband connection, so I could just start downloading those beautiful images of the BSD operating systems and start trying them. At that time, I also started to manage for the university a project called FreeOS-Zoo. And the FreeOS-Zoo was a project where people could contribute sending ready-to-use virtual machine images of free and open source operating systems. And people could just download them or run inside a virtual machine, so they didn't have to get all the problems of installing, repartitioning. It was quite difficult those times to make operating system coexist in those drives. And that project was quite successful, and many people started sending their own images. I remember, for example, Professor Tannenbaum sent Minix images for the FreeOS-Zoo. And in the very last days of the project, another person created a way to launch those operating systems inside the browser. It was launching a virtual machines inside the server and just providing a user interface, a shell inside the browser. It was a very good project for its times. And so I got passionate about all the open source operating systems. But there was a problem. I wanted to study on paper. You know, those screens in 2002 were great for a long time study. So I decided to try to ask my parents to buy me a laser printer, but I couldn't say just for BSD stuff. They couldn't understand it. So I just said I needed that printer for a lot of university papers or university duties. And they agreed. So we bought that laser printer, and the first thing that I printed with that printer has been the FreeBSD handbook. And I started studying the FreeBSD handbook because it was so complete, so full of information, not only about FreeBSD, but about all the Unix systems, that I learned from it much more than all the university studies. So for me, it was something incredible. So no, I didn't use that printer for university duties, but that printer led me here today, so thanks, Mom and Dad. At that point, I installed FreeBSD as a primary operating system inside my Sony Vaio. I had a Sony Vaio at the time. And that laptop was totally transformed by FreeBSD. It was running much smoother, better, faster, more reliable, more stable than with Linux. Sounds incredible today, but it was that way. And I wanted, you know, I was young, I was passionate, I wanted more from that. So I didn't use KDE from the packages. I used to compile it from ports because, hey, after 18 hours of compiling time, I could shorten the boot time of half a second. So, you know, I needed to compile it. So I remember entire nights with that laptop 1 meter away from my head because I was at university, I just had a room, with those fans spinning during all the night because, hey, I'm compiling KDE. My homies thought I was crazy. Maybe I was, but yes. Okay, let's go on. That led me to really consider BSD operating systems as great operating systems. So when in 2003 I started to prepare my final thesis for university, I had no doubts. I decided to concentrate on open source virtualization solutions, especially NetBSD-CAN. I found NetBSD-CAN as a perfect combination at those times. It still is today, but at those times, I thought it was the best open source solution to virtualize environments. And it's been a good, a good choice because I could use it, but we'll see it later, and it really worked out. So let's go on. Years are passing. I graduated. Great. I started searching for a job, and of course, I tried to search for a job where I could use my passion for open source operating systems. So I was glad when I found a company that was starting to deal with Linux. I thought, well, I'll bring the BSDs sooner or later here, but I start with Linux. I'll get into it then. But the problem is that I started making servers for them, so mail servers, web servers. They were creating Java CRMs, so Tomcat, all the stuff that we used to manage in the early 2000 years. And I had to face a problem I couldn't expect, because I was so passionate. I'm trying to do my best. I want to show the world that those open source operating systems can do anything and better than the closed source Windows solutions. So one day, one of the managers called me and started to complain because my servers were too stable. My servers weren't breaking. My servers didn't need constant intervention. As he said, that the clients were used to all the old Windows servers, that the blue screen of death, oh, we have lost a drive, calling them from time to time just because they needed to get back in track. My Linux servers were stable, too stable, and that was hurting the company's billing. I was shocked. I was sad. I didn't want to work that way. I want to solve problems, not to create problems to clients. And unfortunately, when I see a client and see the client has a problem, I want to solve their problem, and I want to be sure that I do my best to solve their problem, not to do my best to fill my pocket. So that wasn't perfect for that company's billing. So at the same time, in the evening, I was teaching Linux courses to system administrators that were experienced with other operating systems like Windows or proprietary Unix systems. And one of those tried to suggest to me, you're young, why don't you try to make your own company, make your own business? In Europe, it's quite different from the American style. We have many small companies, one-man band. We like that. And so I reasoned about it. I never thought I could do something by myself. My idea is I graduate, I'll go into a company, I'll bring my expertise there. And I started to understand which kind of company would I like to create? Which kind of guideline would I like to follow in the moment I will create something for myself? And the base of this idea was make your own kind of music. Don't look at the others. Just understand what you want to do. Understand what you want to provide. Concentrate on them. So it's been 20 years ago this year. So it's been a long time, quite a long time. And I started to define my philosophy. And my philosophy has always remained the same, with several degrees of adjustment. But the point is, I solve problems. I don't sell boxes. You will never see me proposing, this fancy box with all the stickers, bells, whistles, and everything. I will always concentrate on trying to select the best solution I can provide to my clients. And I will do it myself. I will not ask others to provide services for me for that. Maybe I can ask others to work on that, but nobody will ever tell me what I have to do with my services. And this means I will never be tied to any particular vendor. Yes, I can suggest solutions, even closed ones if needed, but this means you'll never see me. I'm certificate seller of this, I'm certificate technician of this. No, sorry, I'm free. I will not do that. So this means that I will always promote open source solutions every time I can, and mostly BSD-based ones. As a fallback, Linux One are good too. So that was the initial philosophy. I decided, I started, went to clients proud, happy, young, energetic, but I had to face the real world. And the real world is, what? Open source systems? But those are just toys for university. The real world is powered by, commercial, expensive solutions. Licenses are something we should consider when we prepare our budget. And it was hard, because clients didn't want to listen, because I was a strange voice in a world dominated by people saying, you have to buy my product. It's expensive, but it's better than that, more effective than that other. So I started to try everything I could to push people to try my systems. I proposed to delay the payment. I'm going to work for free. In 1 year from today, you will see how much you have saved in license costs. You will see how much you will have gained in stability, and then you will pay me. Maybe it was crazy, but it worked. Some clients said, OK, if you're confident enough to provide free services, who am I to say no? And we started to do this way. And this way was using the BSD systems where possible, using NetBSD-CAN as virtualization platforms, and that worked. One of the most successful blog posts on my IT Notes blog, and that is still being read over the time, is that old NetBSD server that has been running unattended for 10 years. It was from those times, and it works. It works. So NetBSD-CAN as virtualization platform, OpenBSD when I needed network, firewall appliances, something that had to run to be secure, to be upgradable without any problem, and FreeBSD for the other services, so backup servers, mainly at the beginning to convince clients that wanted to Linux. I said, OK, let's make a Linux prod server, but let's make a FreeBSD backup server or FreeBSD secondary server. Just have a look at it. Then you'll decide what you want to keep over the time. And they usually choose FreeBSD. So things were working. Things worked out. The clients were surprised both by the stability, reliability, and the easiness of the upgrades. They were used to, we had to restore everything 3 days down. Oh, we will have to restore database. It will be a mess. Buy new hardware. Let's start from scratch. My upgrades usually were, OK, tomorrow from 8 in the evening to 9, I will stop the servers just to upgrade them. And at 8:15, OK, we have finished. Everything is fine. You can go back to your work. Clients were quite amazed at those times. And because of that, there was something that I could really not, outside of any business plan I could do. Clients started to complain, everything is working, everything is stable, why should we pay you? Because they were used to those old problems. I called the IT man because we have a problem. We have a stuck server, so it's freezing, so we need you. They're not used to pay people because things are working. So that has been quite hard too. So I tried to choose clients that could understand the value of saying, no, you don't have to pay me because things are not working. You have to pay me because I will make sure that things will be working for you. Your business is not making systems work. That's my business. Your business is use those systems for your business. Because my clients can be both IT companies or non-IT companies, but they just want their servers to work. So I had to point out many times, I solve problems. The problems I have to solve is not to have problems with you, not to have problems for you. you should continue working always and in a reliable way. It worked. I could have 65% of servers based on BSDs, old BSDs, and 35% of servers based on Linux. Sometimes I needed Linux. Clients wanted Linux. That was OK. I refused many times to put my hands on Windows servers because when I did it, I always did a mess. I'm not a Windows man, so I don't want to put my hands in a totally different operating system. I could just, no, sorry. So over the times, things were working. And Linux started to be everywhere. People started to understand the concept of open source of Linux. So people started to request Linux. Even when we had BSD workloads that were stable, reliable, and so. But why can't I have Linux as my friend, my colleague, that other company, the Fortune 500 companies? So sometimes I had to replace those servers with Linux-based ones, especially the virtualization ones, because clients, of course, wanted to have more control on their virtual machines. So they loved to have a user interface that could launch inside their browser and just reboot or enlarge their virtual machines. So I started to use, at first, OpenNebula with Gluster file system. And Gluster file system has been a terrible experience for me. Almost killed me. And then Moose file system, much better. And then eventually I switched to Proxmox. It was something like 2013, so many years ago, much before the VMware, Broadcom, and so on. At first, mainly with Ceph, the network file system, then mostly with ZFS, because I didn't find for the workloads I was managing advantages of using those network file systems. Yeah, HA, but I found that having more moving parts didn't give me more reliability. But actually, it was less for my workloads. So it was OK. That's a win. The open source is everywhere. Linux was accepted. I could push the BSD systems when possible. We won the war. The open source war, not a toy anymore. People were seriously considering my proposals when I was going to say, let's use Linux, let's use the, oh yeah, why not? You have a great experience in Linux. Yes, I was using it when people were just saying it was a toy, so I have. So the proportions changed, and Linux became predominant. I continued to use the BSDs for my own workloads, for services that I was providing to clients, for example, mail hosting, web hosting, if they just need a interface to upload their public HTML, sorry. They don't care if I'm using Linux or one of the BSDs. So when I can choose, of course, I choose a BSD. But it was OK, and it has been OK for some years. But years pass, trends change, the IT world changed, Hive changed. So I started to understand the situation I was living. So in 23 years now that I've been using the BSD, I never lost a single bit on any BSD workload, server, client, any BSD system. Of course, I deleted some files. I had to roll back from a backup because I did something or a client did something. That happens. But I never had a corruption, a critical corruption that led me to restore something because of the operating system, because of the file system. While I had it with Linux, with X4, more than 10 times, I'd say. With XFS, it's been the worst because it was just for some files, but the client was quite demanding, so it wasn't hard to say, OK, let's recover from the backup. Why? It shouldn't happen, I know. And Butterfile system. Butterfile system, I lost 50 terabytes. It was a backup server, actually. 50 terabytes of data. The disks were just a mirror, so just mirrors. I just rebooted the servers. No problems on the disks, no problems on the operating system, nothing, no upgrades, just a reboot, file system is unmountable. I could not remount it. I didn't waste too much time. I called the client. It was a secondary backup server. The primary one was already on FreeBSD and ZFS. So I said, let's make this FreeBSD and ZFS too. And the client said, of course. And more, FreeBSD is a great, even if not that known way to mount the root file system in read-only using UFS. You just install FreeBSD in UFS. You just change the RW in the FS tab to RO. And FreeBSD, this is a part of the NanoBSD times. And this will lead to a perfectly working read-only FreeBSD file system. So for strangest system, maybe they have not reliable power, or people just unplugging the cord. This happens too. I just create the root file system in read-only, so nothing will break in case of an unclean shutdown. And maybe the workloads or the data will be on a ZFS, but at that time, I can always go back to the server. I can always connect to the server without having physical access to the machine. So I can get in and debug problems. Never had any problem with ZFS, but you know, never say never. So those were things that I was considering some years ago. And more, in 2018, I started to introduce Docker to devs. I wanted to make devs more powerful, you know, free to implement, to deploy things. But this led to problems more than advantages. Devs started to put in production outdated software. Oh yeah, I had to create a container with PHP 5.4 or 5.5. What? It's the only way to make it work. Sorry. No, not on my servers. But it's container, it's inside a container. Don't worry, it won't hurt. It will. So, or I need to run this service as root. But it's an old service. It's outdated and as root. Yes, I need. So I understood that this led to problems. And more, the development of Linux, and both as a kernel and distributions, is evolving towards data centers, big cloud providers, not the small company, not the company that wants to host their own email or their website or their databases, their own data. So that's not the spirit, I remember, of the early days of the operating system. And that's not the way I'm focusing, because my philosophy is totally different from that. So, you see, people just focused on replacing the old with the new. Is the new solving new problems? No, it's creating worse problems, but it's new, it's shiny, it's different, okay. But if we are replacing something that is working and reliable with something that isn't as reliable as before, what's the advantage of that? Why are we doing that? Okay, we're IT people, we love experimenting, you know, I'm a nerd, sometimes my wife, it's time to get to, no, I'm just trying a new release of that software. We are IT people, but our clients are not IT people. They want their website to stay up and running. They don't care if it's running a brand new software or a stable and reliable HTTPD from OpenBSD. That's the point. So, there's no one size fits all. And the current trend, especially in the Linux world, is this. Let's just go to the cloud. Let's just go to the Kubernetes. Oh, I have to put a hello world page, HTML. Yeah, we create a Kubernetes cluster for that. What? And that's why I'm creating blog posts on my IT notes saying, you can do your personal blog with tens of thousands requests per minute on a €1 per month VPS. Because we can. Why should we give up this freedom, these possibilities? We shouldn't. So, solving problems for me means creating solutions that will reduce new problems, not making them worse. And clients, as I said before, don't care if their website is powered by Linux, FreeBSD, OpenBSD, NetBSD, Illumos, or whatever. They just want it to be reachable, secure, stable, reliable, backed up in a consistent way. So there isn't a single solution to all problems, like several companies or consultants want us to believe. But there are tons of solutions for a single problem. So my job is to give those clients the solutions I think it's more appropriate for their specific problem. So I stopped and thought, okay, computing should solve problems. We're not using computers to create new problems. Unless we are doing that for business, let's create problems so we get paid to solve them. But that's a different topic. I solve problems. And here solving problems is choosing the best technical solutions I can. So the BSDs are stable, reliable, upgradable, secure, and clients want that kind of approach. They just don't know it. They just don't know what they want as a technical solution, but they know what they want as a result. So it's time to get back to the BSDs, to reverse that proportion again. Go back to the most BSDs, and Linux has a fallback. So I started to propose clients the BSDs for different tasks. So OpenBSD, when they don't need anything else but the base system, OpenBSD is a great base system. It's consistent. All the configurations are, if you know how to configure PF, you can configure RelayD, you can configure HTTPD. Configuring a network interface in OpenBSD is beautiful. And people sometimes, is it all? Just writing some lines in a text? Yeah. But no systemd? No. Nothing fancy, you don't have to make several clicks, no. Just one line, and they will keep working for years. So OpenBSD, the first choice when I have to make a simple system. Simple doesn't mean that isn't powerful. Simple means easy to manage and upgrade. NetBSD is used when I need to create setups for specific hardware or for workloads that we cannot touch often, like places connected in an unreliable way, or just for internal services monitorings. And that's good, because NetBSD doesn't need to be patched that often. So it's a perfect choice, or if using, of course, one of the architectures. I am powering my own IT nodes blog. I have some varnish caches nodes on some cheap VPSs, but the main two public HTML directories that are powering my blogs are on OpenBSD Amsterdam VM and a Raspberry Pi W first edition over my bench, powered by the USB coming out from my switch. It works. I can upgrade it. I've never seen any slowdown. Yes, of course, I have the varnish caches outside, but never had any problem with that. And I have my blog 1 meter away from my hand. So this is quite strange today. FreeBSD. No need to say ZFS, Beehive, jails, and so on. I'm keeping an eye on Hammer 2 on Dragonfly BSD, but I haven't any of them in production at the moment, so I can't say much about that. So let's go. Let's start migrating back to the BSDs. How? At first, I decided to migrate the workloads, so virtualization servers or virtual machines that needed some upgrades or was showing some problems. So at first, I decided to make a fair comparison between the traditional Linux setups and the BSD-based one. So I decided to create some twin machines. And for twin machines, I mean many of my servers are leased inside European data centers, European providers. So I could lease a twin machine, a machine having the very same hardware configuration, and start installing FreeBSD and moving the workloads, both in form of virtual machines, so from Proxmox to Beehive, or just replacing the services, reinstalling or reconfiguring inside some jails. And what I noticed is a significant increase in I/O performance. In Linux, in Proxmox, I've always seen in any hardware setup, even the most powerful ones, that when the physical node is struggling with I/O, the virtual machines will hang for half a second or something like that. And when this becomes problematic, they will complain about, hey, I couldn't write on the disk for more than 1 second. And this is a problem. I never saw something like that on FreeBSD. In the I/O weight, I mean, I'm not talking about the number you see when you go to top, but I mean real world use is managed much better on FreeBSD. And ZFS is making this even better because the caching that is performed by ZFS will make everything snappy, even if on spinning disks, not only on solid-state drives. And this is a huge advantage. Of course, there is ZFS on Linux too, but I don't want to rely on something that I have to compile or hope that will be compiled at the next update cycle. I want something integrated inside my operating system. And FreeBSD ZFS is a perfect combination for that. So after seeing this, I did something crazy, but not that crazy actually. I decided to migrate 2 physical servers of a client. Each of them contained more or less 10 virtual machines over a weekend, same hardware, from Linux, Proxmox, to FreeBSD, Beehive, just moving the virtual machines from one host to another. Before anyone will complain about that, I've been criticized in Dublin for this. Someone said, you're crazy. You had to inform the client. Of course, I'm not totally crazy. I did it because I had an agreement with the client where I just provided the services. They know I can move the virtual machines from one server to another or something like that. So it was OK. But that was a test because I wanted to avoid any kind of bias. You know, hey, client, I'm going to upgrade your server. The day after, oh, yeah, it's faster. Or the day, it looks slower. If they don't know anything, they usually don't notice anything. So I performed this test. Over the weekend, I started to migrate the first host. It was easier than expected. So I proceeded with the second host. So all the virtual machines were migrated. On the Monday morning, I was there looking at the phone. Silence. Nobody calls. And when a client doesn't call after such a migration, it's a huge success. But on Tuesday morning, my phone rang. I was a bit, shocked. Oh, well, what's happening? The client was worried because they noticed a massive performance increase, and they thought I had upgraded their hardware. And they were worried, how much will it cost to us? This is the best thing that could happen, actually. I explained to the client what I had done, and the client just said, go on, let's migrate all our 20 physical hosts to FreeBSD. So I proceeded, but then I optimized things. So I decided that some virtual machines could just become FreeBSD jails, and that way, I could save resources, because having jails instead of virtual machines meant no double buffering, saving RAM, because I didn't have to assign a specific amount of RAM to the specific workload. So the jails were happy, or better, the services inside the jails, because they could use all the RAM of the physical host. So databases were happy, ZFS was happy, client was happy, and moving from the VirtIO virtualization driver in Beehive to NVMe made a difference in performance. And I also wrote about it on my blog. So this led to a massive reduction of the number of needed hosts from 20 to 11. Same workloads, same hardware, same better performance, almost half the physical nodes needed to do this. The client was happy, but I was more than happy because my ideas, my philosophy was working, was proving I was right. We have to get back to the BSDs. And then I started to propose devs to move from the Docker approach to the jails approach. And this was good because younger devs didn't even know they can use something different from a Docker Compose app to deploy a workload. And that's a problem, because they're now used to think that they cannot host their own services. They need a big cloud provider. They need to pay for the use. Just many of them, not all of course, but don't understand the power of having the control of their own data. And this led many of them to explore this new, old way of working. And they were quite excited about it. So, in some cases, they requested, how can I access that specific database? Put your cloud provider here. I have an API to get the data. Here you have the dump. Just copy it inside your private drive. You have all the data. For them, it was crazy. But it worked. And they started to request more and more FreeBSD jails. Because the problem often is not technical. The problem is ideological. People just don't know about BSDs. People just don't know they can do the things in a different way than the ones they found when those beautiful jackets, oh yeah, I can sell you this beautiful solution, thousands of dollars per month just to have a Hello World page there. And our task as BSD people is make people aware of this. People should know that there are different solutions. People should never try to fall into monoculture. Always have a backup plan. And clients are often influenced by the hype. Kubernetes, everybody's using Kubernetes. Why aren't we using that? You don't need that. You don't need a truck just to bring a bag. And that's what I'm trying to make people understand. But, you know, the trends are different. AI, Kubernetes, blockchain, Linux, complete as you prefer, but, you know. And simple solutions are usually the easiest to maintain in the long run. Maybe you need some more time. It's not a Docker Compose app and you're there. You need to create the services, the jails, everything. But once you have the services up, they will run. They will be upgradable. And in case of problems, you can just spot the problem. It's not inside a stack you can control. Sometimes I read those, Docker files, and really look at my hair. They're all fallen because you just see they're gluing pieces together, outdated software, just patching everything, and it's working. But don't try to do it at home. It won't work. So I can trust something like that. Because I want people to always own their own data. We need to own our data and avoid any lock-in. I don't want a client to say, I have to use your services because I'm locked in. No. If we have not a good relationships, here your data. Go. Thank you. Because I think this is a way to deal with people. And we are people dealing with each other. So, the BSDs are conservative. And conservative is good. It doesn't mean they're not moving, but they're moving in a wise way. After my presentation in Dublin at EuroBSD conference, Liam Proven wrote a beautiful article on the register, and he perfectly understood the point. He said, they're moving to the BSDs because the BSDs are boring. Yeah, I want boring operating systems on my servers. Because I want to be bored. I want to upgrade them when I'm doing something else, or just, yeah, okay, it's working, yes, that's fine. I don't want to, oh, it's not booting, what's wrong? And every additional layer can bring more problems, because more code doesn't mean less problems. There are more probabilities of problems, bugs, security issues, and so on. And OpenBSD, for example, the OpenBSD OTCs, everything has changed, but nothing has changed, and that's a good approach. We have to evolve. We do not need to change everything just because, hey, that's old, it's wrong. No, that's old, well, let's make it more, current with the times, but not replace it just because it's old. So this time, I solved problems, And I solve problems by not overcomplicating stuff. Clients call me, I need this new, web server, my e-commerce, WooCommerce, Magento, or anything. Okay, let's make 3 jails: web server, database server, Elasticsearch. Stop. That will be working for years. We just upgrade everything when needed, and the components will be separated, not glued together, or who knows where in the cloud. The BSD systems are stable. No surprises after reboots. I upgrade a server, I reboot it, it will start pinging back in a couple of minutes. You never are surprised, like, for example, I rebooted a Proxmox server and it wasn't reachable anymore. I had to connect to the virtual console because I could not reach it anymore. What's wrong with that? And I found that it renamed that to that after a reboot. Why? I want IX0 to be IX0 after 100 of reboots. Why do you change my... People replied when I posted it on the Fediverse, and people replied, there's a good reason for that. Okay, I'm sure of it. But I don't want that. I'm sorry. I want IX0.
There have been instances in BSD where on a multi-port box, a minor version upgrade flipped the ordering.
Yeah.
We're not immune to it.
Not totally. But I can assure you that on Linux it's much, much, much worse and more common. So, yeah. And as I said before, ZFS, I want ZFS to be integrated. I don't want to recompile ZFS every time I upgrade the kernel. And then, because I tried that, I've been hit by that, I'll not do it anymore. So, and I don't want to tell a client that specific architecture of that specific device you're using because it's certified for running at 150 degrees won't be supported anymore because it's an old architecture. I'll just install NetBSD on that, and I'm safe. And the client is happy. Sometimes they even forget they have those devices. They're so used to see them working that they forget about them. And that's the best thing that can happen when you're deploying solutions. So, current situation. Many devs embrace the challenge. They are now happy to use BSD-based solutions, and they bring other devs to the BSD solutions. So the BSD adoption rate among my clients and the friends of my clients is increasing month by month. And for me, it's a joy. And when I see an email, last one yesterday morning, I received an email morning in Italy. Here it was, well, okay. I received an email, I need 3 jails when you'll be back from Canada. When I see I need 3 jails, it's music. And this way, they learn to manage the resources. Because just doing Docker Compose up, they lose any control on how much memory the database is using, how much space that specific server or service is using. They use the cloud, just pay more. Oh, the service is low, we need more power. We need to increase the resources, just pay more. But if you're just doing a select of 3 records, you can't use 1 gigabyte of RAM. There's something wrong there. But you can't spot it easily when you're in the cloud or you're not controlling the whole system. And this is what still helps to give clients a 30 euros per month server that is an e-commerce that will serve the whole Europe without any problem. And that's the point. I'm managing some servers for some clients that are selling all around the Europe, and big numbers. They're doing big numbers from a 30 euros per month physical server. We have 2, actually, so we can ZFS send and receive every 5 minutes as a fallback. But 60 euros per month to make 10th of euros per day, they're happy. They should pay me more, actually. Okay. The clients are happy. Nobody asked, let's go back to Linux. No, 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 let's go on with the BSDs. And I explained, some of them actually became advocate for trying to avoid the monoculture. So that's great. And they value the stability and security of the BSD systems. The problem is more with the managers. The managers have to sell those services. And, you know, Linux sells well, NetBSD a bit less. It's hard to explain those sellers how to sell good solutions.
You're selling white label cloud services.
Yeah.
You don't mention the OS.
Exactly. You usually don't. So that's the point. But many of those managers want to use the buzzwords. So why should I sell FreeBSD? There's no Linux, no Docker, or at least not that used. No cloud, no AI, no distro wars. It's so bland, so boring. But we should sell boring stuff if this is what they need. And that's another problem, compliance. I sometimes receive emails, oh, your OpenSSH server is not compliant. Oh, well, it is, it's OpenBSD. Latest release, don't worry. Yes, but it doesn't contain that string. Yes, but Debian is something else. I can't see it in my checklist, so I cannot accept it. You know, and that's a problem, because those people doing those documents are usually unaware of the BSDs. Actually, they're usually unaware of any kind of technical solution, but you know, that's the point. So the current situation, I'm a bit out of time, but you'll be patient too. I'm verbose by design, so default. At the moment, mid-2025, 83% of the hypervisors I'm managing are powered by FreeBSD. And I find it a great result, considering that I started 5 years ago, more or less, and the FreeBSD hypervisors were much, much, much lower in number and in percentage. So things are being great. And I'm doing this week by week. 72% of the workloads, so VMs or physical servers, are powered by one of the BSD systems. OpenBSD, FreeBSD, NetBSD, it's a general number. And clients are requesting many setups based on OpenBSD. Because when an SSH vulnerability comes out, and they call me worried, we have to patch as soon as, don't worry, OpenBSD there. It's been patched in 2001. They just are puzzled. Why are we use OpenBSD for anything? So I want more OpenBSD here. OK, we are here to help you. Others love graphic user interfaces. So OpenSense is a great choice for their firewalls, for their routers, for anything that they want to control in a direct way. And the FreeBSD jails are great for devs that want to get out, the passionate ones, not the ones just having, you know, a job because they have to eat, but the ones that are passionate about their job. So which are the next steps? Because we never stop. Sorry, you will stop me when I'll be dead. So I want to go on with the BSD-made service. I've announced it more than 1 year ago. I'm still working on it. I have some more bureaucratic problems than technical ones to launch it. I have to understand some problems because it will be a worldwide service. And entirely based on the BSDs, OpenBSD for OpenSMTPD, and FreeBSD jails for the other services. So Dovecot, replication of Dovecot between two hosts, it's already up. BSD Mail is already been working for me and my emails for more than 1 year. But that's for me. It's different to launch it in a wide way. But it will eventually come because we are depending more and more from monolithic systems, companies, services. Internet has been great because of its decentralization, and we're losing it. We're just concentrating all the services on big companies and players, which could be okay for some, but why should we lose the possibility of decentralization of the network because of this? Yesterday, there's been a great problem. I've read that many cloud providers have been down for some hours. I don't know. I didn't notice it. I'm not using those services. No client has complained. We were just having a dinner with friends. No problem. And clients should appreciate what we do, what we provide, not lock-ins or ties. So that's what usually brings clients to us. We're providing solutions that they're not aware of, but they know that they are working, and they are the BSDs. And they feel free. They can go away whenever they want. So I want to reach the 90% of the adoption rate of the BSDs, and I hope to reach it by 2027, so just 2 years. I'm not saying 2026, but I hope so. And I want to continue to advocate for the BSDs using the BSD Cafe, more about this in the future, but also my IT Notes blog, where I document ways to do things in a different way, not Docker Compose app, but how to install Uptime Kuma on FreeBSD even if it's not officially supported, which is not a hack. It's just a way to show people that they can do the things in a different way. And they can choose. Maybe they prefer the Docker way, perfect, but they should know that there are other ways to manage things. So, I'm finishing. The transition to the BSD is going smoothly, much better than expected. I expected much more, having lived the early days 20 years ago of the open source adoption, I thought the clients would have been, oh no, let's just stick to Linux. No, clients are quite open now. They're accepting the BSDs in a passionate way, and when they saw them, they wanted more BSDs. Clients are satisfied, devs are satisfied, we are satisfied, near to zero alerts waking up us during the night for critical servers, for the BSD ones, at least. We'll continue to provide solutions and not boxes. We'll continue to go on with that philosophy that has been set 20 years ago. That will be the same for at least the next 20 years or 30. So, no closed box, no shiny solutions, but to sum up, I am Stefano Marinelli. I solve problems, and I love solving problems using the BSD systems. So, thank you. And I hope you will all come to BSD Cafe. We're waiting for you.
I noticed something recent, which is the opposite, something going from BSD to Linux.
Yeah?
Which I find really annoying. Is anybody else annoyed with IX systems changing TrueNAS to be only Linux?
This is a hot topic here, I guess. Yeah.
I embrace TrueNAS because, it gave me jails, it gave me Beehive to run some VMs, and ZFS native, and all that other stuff. But
Yeah. That's why I usually try to stick to FreeBSD by itself, OpenBSD, and not products built over, because they could eventually change their their path sooner or later. Yeah. Sorry.
The title of your talk is how you're migrating many of your servers from Linux to the BSDs, but not all of your servers.
Yeah.
So I was curious, are there any actual technical reasons you come across to actually stay with a Linux-based system?
Sometimes there are. The problem is that not all the services can be migrated to the BSDs because they are not compatible with the BSDs. They're not running there. I'm usually getting over it using the Linux simulator, which is giving release by release better results. So many of them can be switched now that maybe could not be switched 2 years ago, for example. And in other situations, I have to install a specific software the client needs, like, for example, Zimbra mail system, and they run on Linux. So, of course, those Linux virtual machines will run inside Beehive, so FreeBSD as a host. But, this requires time as I'm managing hundreds of servers, so I cannot switch all of them from one day to another or from 1 year to another. But usually the problem is more, as I said, ideological than technical. So that's the only reason why. Otherwise, I'd just move. I have some problems with my laptop or desktop on the BSDs, but that's another topic. Welcome.
Yeah, my story is
The flickering is not my thing.
Okay.
I checked. Hey, Albert, I can hear myself, so presumably that's working. And the real question is this going to cause a problem? Can you hear that if I do that? A bit, but I'll try to not do that too much. Yeah, exactly. Yeah. I was just concerned about the, Yeah. But yeah, no, the flickering is not my thing. Apparently it was happening yesterday. So, yeah, be what it is. It's starting to happen more and more, those too, so. Yeah. I mean, I'll double check it, but yeah. Yeah, it's at 1080. 60. I could drop it to 30 though. Well, see if that works. Yeah. Oh, there we go. Refresh that. And we'll see. Maybe it's that. Yeah, exactly. Well, the thing's being recorded at 30 anyways. So. Yeah. All right. First slot after lunch. Supposed to be starting right now. I'm going to give it like 1 or 2 minutes, but start to either make your way out or sit, say hi. It is the first slot after lunch, though, so I'm going to give it probably 1 minute, 1 or 2 more minutes. It's currently 1:16 according to this. Anyways. All right. So thank you all very much for being here and deciding to listen to me yammer on about stuff. I appreciate it. And more to the point, hope it's interesting. We have about, so first and foremost, my name's Rob. I have been asked to repeat the questions if you have a quick one. I will happily answer questions if you have a quick question. And otherwise, there'll be a mic going around afterwards. Other housekeeping, this is roughly, I think, 28 slides in a 50-minute thing. It's going to go rather quick. There's a lot of content. That being said, it is meant to give you a, hey, look, this is a thing, also all the way through. There'll be an agenda, like a, here's what we're going to cover. I just wanted to be clear about, there'll be a lot of content. The slide deck will be made available afterwards. So if you're interested in this, you can find that information later. All right, let's just jump in then. So we're going to go over why would I bother doing this? Like, what are we doing? Existing alternatives and why they don't fit. We're going to go over Fuse, Elixir and the Beam, consensus algorithms, Raft, and a demo, and then questions. That's a lot to cover, and to be very blunt, it's a high-level overview to get to the putting it all together. So for the few people in the room, and honestly most of you, distributed operating system using Raft as a consensus mechanism, using Elixir with Fuse. That's what I did, and that's what this talk is about. So, getting a little bit more into it, what's the point? Why do this? Most people here have a few servers. Most people have servers that probably talk to other servers. I happen to run servers that talk to each other and are geographically distributed, and I wanted them to have the same state. And we'll go over there are many ways to do this with no problem. But at the end of the day, I am getting a little bit of feedback. It'd be nice if that could be turned down just slightly, but it's not the end of the world. Hey, that's great if you could do that. Awesome. Okay, I'm glad I asked. Anyway, so I'm running a small Anycast system. There you go. I needed to keep state. I did it a few different ways, but this is about using Raft. That's what I'm solving for. 1 out of 3. Alternatively, take your pick. If you run Quorum, you can run, 2 out of 5, let's say. But I'm solving for basic Quorum. And the idea is that the machine could go down, and then it could come back up at some later time, and I could recover from that. And while that machine is down, everything else keeps ticking along. So it ensures the files, and this is a file system again, right? So you can do this with a bunch of different things down to a file system. No single point of failure. All nodes have the same software and roles. This is a big one because you can solve this with many different ways. I wanted a solution that I could deploy one-to-many in terms of a configuration and in terms of like my software bundle, let's just say. Has to work on OpenBSD, and I don't have any serious performance concerns with this system. So by that I mean I'm not doing a serious heavy read or write. Raft as a consensus algorithm dictates that you have one reader and one writer at one time. That's how it guarantees consistency. So there are other systems that don't do that, but you are basically, with this system, sacrificing performance for reliability and availability within certain constraints. And yeah, so single writer is fine. Offhandedly, those are some of the existing alternatives. So first and foremost, run S3FS and MinIO, or take your pick of whatever else you want, like Ceph or distributed file system. That would be what most people reach for. That's what I reached for. It doesn't work with OpenBSD because of the Fuse version. And one thing I've taken away from this was that I should have just got my hands dirty and bumped the Fuse version that was available, because it would have been a lot easier than doing what I did. You can also do a change of architecture. So with OpenBSD, pretty standard stuff to run pairs, right? So carp, and you could use iSCSI or block stuff to do pairs and NFS over that. People are running kube on OpenBSD by way of like a VM, right? So putting a single core and then running Linux on that. You could do that and it would work. I didn't want to do that. And then the crazy thing that I did that I talked about earlier at a different conference was basically block iSCSI devices, block software RAID, carp, and NFS to get the same functionality. But that resulted in a lot of complexity and a fairly high chain of stack, and more to the point, the machines were different. The machines didn't have the same roles at that point. It becomes really painful if you have different disk layouts. Yeah, would not recommend. Don't do that. So we're going to rip through this really quick. So pace is going to be picked up. File system user space allows for programs to define file systems. Those are some of the things it does, etc. Basically, you interact with the file system, and there'll be a diagram next. And it goes into your program. Your program decides what happens. It's fairly flexible, and it's not as performant. You're going down and back up on the kernel, right? So it's not as performant. Go figure. That's what it looks like. That's probably more useful to most people in the room than the slide before it. Basically, down and up. Your application hits something, and your application defines file system. Different applications, that is. On OpenBSD, was added in 5.4. It is Fuse version 2.6, and there's also, it's worth mentioning, if you get into this, Fuse has two different versions. It has a kernel ABI version, and it has a public version that it talks about. Those are not easy to separate. But the bottom line is there are some things and packages that already exist that use Fuse. So SSHFS, exFAT, and UnionFS does what it says on the tin. And the one thing I would look to note is UnionFS is kind of neat because it does it based on directory, not based on anything else. And so you can do stuff like, have a remote NFS mount and actually do UnionFS on top of that, so that you can actually do your storage is over there. But if you can use mix and match. Bottom line is, though, if you look at other operating systems, the list of packages for Fuse are much, much larger because of the Fuse version. And that's just simply nobody's had time to look at that and do it. And there hasn't been a demand, presumably. I should have done that. Oh, good. I did actually put that in. We're going to go really quick through this. There's a lot of stuff about Erlang and OTP and Elixir. This is a stack. There's going to be a diagram on the next slide to give you an idea. If you're not familiar with Elixir and Erlang, it is an ecosystem that's really nice, comes out of Ericsson a long time ago. It's adopted by a bunch of different things now. And I'm not going to go through all of these points, but the basic idea is you've got a stack similar if you don't understand or don't care. It's not the same, and there are people who are going to really care, but for a high-level overview position, if you're familiar with Java, there you go. There are things that are packaged up along with a VM, and it is a VM. It does have bytecode, that kind of thing. Yeah. So, and Erlang and Elixir are the languages. They do have Lisp in there as well. The big thing here is kind of the overview. So you've got a stack, and your applications run on the top. And in the Beam and these languages, you have a lot of processes on top. So you can easily have tens of thousands, hundreds of thousands, millions of processes that are Erlang or Elixir processes that live on top of that language. And so those would handle things like a single HTTP request, let's say, is a very common use case, or a single TCP stream would have a process dedicated to one particular stream. For our purposes, package add Elixir. That's really high level, but that's really basically it. It gives you the entire stack, and then you can write programs. There's a thing, I really wish there was a diagram I could find on this. I didn't have time to, well, I didn't prioritize putting a diagram here. That ecosystem has an idea of ports and NIFs. And ports are, as they say, separate processes, and they communicate standard in, standard out. So it's a way of saying, it's basically the foreign function interface. Let's just say that. It's not correct, but it's close. You can run arbitrary programs as a port, and then talk over standard in, standard out to that program. And you can't crash the beam easily. And that's important because basically the Elixir and OTP stack are designed to handle failure gracefully. All of these processes I was talking about at the top, the whole point, well, not the whole point, but one of the major points is that you can actually have one of those processes crash and the entire thing doesn't crash. This, using ports, allows you to, if your port crashes, it doesn't crash the beam. And so for certain workloads, that really matters. NIFs are compiled and linked in, and they're more performant because of that. You don't have to go through that channel, but you can crash the beam. And because of the synchronous communication on there, you can actually, there's a whole bunch of, as you can imagine, you've got, say, 10,000 processes way up the stack in this VM. There's a scheduler that exists in that massive stack I'm not going to go into. That scheduler is really important because it actually makes sure that all the stuff up there works, right? If you write a NIF, you can starve the scheduler, you can do some bad stuff, and you can crash the thing in a few different ways. Okay, say it with me. Consensus algorithms are not discovery mechanisms. They might include them, but they are not the same thing. It's a very common misconception. So just right off the bat, this is not about how nodes find each other. This is not about how systems discover each other. This is consensus algorithms that I'm going to be talking about are about how do you come to an agreement. So, I'm going to do it on time, not too bad. You can read, hopefully, if you can't, there are some screen dictation software things, but the high levels of this slide are, this is not going to be a deep dive into consensus algorithms. The things that you need to care about is, do you need to handle Byzantine fault? So an actor that is not doing what they should. So if you have 3 nodes, if one of them goes rogue, do you care? Are your systems set up to detect that? That Raft, as an algorithm, is not. It assumes that all of your nodes are acting fairly and properly. You may need to care about this. There's a bunch of different algorithms. Paxos down there is a pretty common one. We'll go into it with one slide. Raft, I think, has 3 slides, and there's one slide about crypto and DHTs just to kind of set them aside. So to get that out of the way, because it's a thing, if you Google consensus or you search for consensus algorithm now, you are going to get a lot of results relating to blockchains and DHTs and crypto. It is the same thing in some ways, but it has distinctions. Most of the time they're dealing with public chains, so they're trying to solve problems that are, if you have anybody in the world being able to talk to this or talk to each other, and we want to agree on something, how do you do it? That is the same problem in a way as what I'm trying to solve for, but it's really not, because you end up with, I have 3 nodes, not thousands or hundreds of thousands, and I generally speaking trust them. So there are different algorithms to do different things. Yeah, and they have different properties. There's the FLP proof, if you're interested in this, by all means, take a deep dive. Consensus algorithms basically comes down to you have to have some trade-offs. You can't have everything. So in an ACE, the point out of this slide is if you you have to have a system, a consensus algorithm has to be designed in a way that can take, assuming that it's asynchronous, it has to have certain properties. Because if it's synchronous, you're all in lockstep, that's fine. If you're async, you don't know if this node has gone bad or it's down, versus it's just taken some time. And so you can't reach finality or termination. You have to put some bounds on the thing to be able to, you have to loop it, basically. You have to have an iterative process. Or you can also just live with the eventual consistency. So in this terminology, eventual consistency is basically, think of it like dirty reads. You can have a system that has 3 nodes, the writer changes one of them, and you read it immediately and you get the previous version. That would be eventual consistency. Paxos. Yeah, lots of stuff there. Tried and true, used all over the place. Big notable ones for this crowd are probably Ceph. It's used a few other places as well. And the original paper is really only a single decision. So there are many variants specifically to handle this. And one of the big things we'll see with Raft was to replace this. Replace being a very, not real replacement. They do different things, but in different ways. Okay. Raft. It's designed to be, and we are going to get to this whole actual file system, I swear. It's just, I'm setting you up with all the steps, right? So we went over Elixir and that stuff. We went over, some consensus algorithms. We went over Fuse. We'll put it all together and we'll be in good shape. So it's designed to be easy to understand. That's, if you haven't looked at Raft, if you don't have experience with consensus algorithms, Raft is the one that is approachable. It's taught in universities these days a lot. Paxos and Raft are the main standards. Paxos being the standard that gets taught traditionally, Raft in the last 10 years or so. It is a strong leader, as I mentioned before. So what that means is, not only is it not BZT or Byzantine fault tolerant, it also, at one point in time, there is one leader. And if that leader goes offline or dies, there are mechanisms that we'll get into very shortly to replace that leader. But when that leader is the leader, when that node is the leader, it is in charge of determining things, which makes reasoning about dynamic systems fairly straightforward. Because you can say, okay, well, at this time this was the case. You have one source of truth, sort of. We'll get into the consensus algorithm itself, but you have one source at one time of truth, unlike a distributed system that you can make Paxos into, where you have many, many, many decisions going on at the same time, and those decisions can be spread across different nodes, which is really good for performance in some ways. It also adds a lot of complications. So I mentioned it has guaranteed consistency. That's where that strong leader comes in. So writes are directed to that one leader, and then that one leader communicates out to other nodes. There are some things there. Reads can be dirty depending on your implementation of Raft, but the default one is that they go to the leader as well. So if you get a read in from a local machine, it'll go, well, I'm not the leader, but I will forward that request over, and then goes, yep, it's the same. So you end up with consistency guaranteed because of that, but you end up with performance issues as a result. It's also on the slide. It's very popular. You are probably running it, almost guaranteed. So it's in Kube because of etcd. It's in Rabbit, Kafka, ClickHouse. The Hashi stack runs it, so Consul, Nomad, all that stuff. It is very popular for a reason, because it trades off performance and a lot of performance really, for understandability. And that's attractive when you're dealing with certain types of systems, or systems that you want to be able to maintain. It is worthwhile mentioning that Raft is designed to handle, your application has to handle certain things, right? So there are properties of it that you have to take into account. I'm going to do it on time. Yeah, 1:30, okay. That's the basic overview. We have a log and a state machine. So clients, as in your program, talk to Raft. Internal to Raft, which is described as that server there, there is a log, and it's append only, is the logic. It's not technically append only everywhere, but it's append only on the master, or not the master. Terminology is pain in the ass, coming from different places, but from the leader. When there's agreement on that log between different machines, and agreement being majority, then it gets applied, and that change gets applied to a state machine. Your reads come out of that state machine. So this is all a very fancy way of saying you have a replicated state machine that has some guarantees. So that if you talk to it, you have a replicated state machine, you have that state that's guaranteed. That's what it looks like, very roughly speaking. So you have 3 states that a node can be in, or a member can be in. Fairly straightforward in the sense that a follower is a follower. It just takes in information and goes, yep, that looks good, basically. There's also I haven't heard from the leader in a long time. I need to maybe become the leader. Candidate in that process, and then a leader. That's it. It's not that complicated compared to many, many other systems. Last few notes on Raft. So there needs to be compacting of logs. So that slide previous, we had this notion of logs, and then those logs get pushed into a state machine. Well, if you run a system for a while, the log's going to grow to infinity. You need to have some way to agree to shrink those back down. That's a thing. I didn't touch on the details, but Raft has a notion of terms. So basically, a term is related to the leader. So there is one leader per term. And the way in which the Raft algorithm works, roughly speaking, is that if a leader fails, or is perceived to have failed by a majority of the cluster will agree on a new term. And that's the way in which you can ensure that everybody's on the same page. There are 2 or 3 RPCs. There are more if you want to, but the paper goes into 2 in the basic paper. It adds install snapshot for 3 otherwise. But the RPCs for the nodes are not too bad. Cool. So now that we got that, we got Kepri. Oh, I swear we're getting there. I designed this in a roundabout fashion to get to the stuff that's fuse. Replicated on disk library for Elixir. Raft is used by the RabbitMQ systems. For a storage mechanism, RabbitMQ usually uses, for stateful queues, it uses an application that's built into Elixir. And that is really nice, but it also has some problems from a eventual consistency perspective. So what I'm referring to is if one node fails or you lose quorum with the cluster of them, the system that comes with the OTP and Beam and Elixir and technically it's ERTS, but it exposes that problem back up to you. So you have to deal with it as your application. So like you want to handle, oh, there's a consistency issue here. That has some annoyances, let's just say. Kepri has Raft basically currently available. And oh yeah, so this is actually related to Rabbit. So RabbitMQ, you can use Kepri right now as a storage system, just behind a feature flag. And the biggest thing as to why Kepri is a pain in the ass right now and why I'm not using it all over the place, although it still is quite nice, is that it stores its contents in memory as well, right now. So not a big file system right now. There you go, there's some more stuff about Kepri. It's really good, highly recommend you look at it. It comes out of Broadcom and VMware and RabbitMQ. But you can change some stuff with it, and there are some details there. It ends up with a tree structure. You have puts, gets, deletes, and transactions, and triggers. So I was at a different conference, and somebody was talking about injecting certain files or hooks where if somebody scanned your system, it tripped an alarm. You could do that with this, because a trigger or a stored procedure is just an anonymous function or a piece of code that runs when something gets accessed or something happens. So that's an application for this as well. So I am way early. I ripped through this, which is good. So it's current, yeah. Pulling it all together, we've got 3 nodes. Each one runs Elixir application in the same code. That is a big piece of why I did this. There are other solutions to this, right? They can find each other. I'm not going to go into tons of detail, but for me, I just went, okay, I've got 3 nodes. They're not going to change that often. I'm just going to push that configuration out to those 3 nodes. You can do that dynamically, obviously, to find each other. Kepri gets started. A C program starts as a child from Elixir, and then it calls fuse main, which is inside the port, as in the C program that gets compiled. It calls fuse, and there you go. So single port based package. So in this ecosystem, there was one package that already existed with Fuse. It's called eFuse and UserFS. They were not mature, and they were Linux specific. I had to not just modify the makefile and include paths and that kind of stuff. I actually had to fix the code as of yesterday. I was like, why is this blowing up now? No, they had a buffer overread. So yeah, also had to implement a lot of the calls. So thank you for the people who maintain ktrace and kdump, because that was useful. I did create a Fuse NIF, and I didn't actually end up using it. It uses Rustler, which is basically, because there's a massive ecosystem of Elixir systems, Elixir has NIFs. If you're bothering to do that, there's some reason why you're adding in code to the beam specifically. You want those things to be safe. And so there are some packages that exist that try and put guardrails around that. Rustler is one of them. It basically makes it very, very nice and easy if you have some Rust code to have it run in Elixir and call it back and forth. So you can go, oh, I want to call this Rust function, and you can do that back and forth. All with nice macros, and it also handles all the type conversion for you. I ran out of time on that, so I started to make it work. All right, so there's the demo. I have a YouTube video, or like a video as a backup, but we're going to do this hopefully live. Yeah, good. So let's see. Let's just load up this. So I have an OpenBSD system here. It has a Fuse file system on it. So what's actually running is, yeah. Oh, even with that, it's noticeable. Yeah. Thank you. Yeah, exactly. Okay, we'll make that nice and big. So on this machine, you've got the beam. It's running. It's running as root because you have to for certain things, as in to spawn a process that then ends up being able to do the thing. That should change. It also should change because that program right here, this one, that eFuse, should actually drop permissions as soon as it gets run. That isn't done yet because I had to make it work. But the basic idea is you end up with that. It defines a Fuse file system, and that Fuse file system interacts like a normal file, right? If I go to a different machine, it's also mounted here. It's a different machine, different city, and it's also there, right? So these files have basic, file D. If you try and do something on this that isn't implemented in your Fuse file system, it will blow up at you and not let you do it. You can also, this is because the port and or the program that is running Fuse doesn't implement that, and so it'll kick back an error. This also means, oh, I'm sorry to the people on the stream because I just touched that mic. It also means that you end up with weird metadata because you can implement git adder. So the program is in charge of all of this. So you can make it do whatever you want at any point, which is great, but it means that you can default to certain things. So you'll notice it's all, epoch 1. So it's also worth mentioning the write path is not actually, you notice I couldn't write to this directory? That's because the write path isn't defined in that one package. And I made the assumption before I submitted this talk that, oh, that's there, good, I'll do this. I solved my problem with another way, see aforementioned NFS and block IO scariness. So for this purposes, I ended up with a write path that is just this. So this is going to one machine. Let's go here. So So Kepri is basically, I can run a command and get all of the stuff in star. It's also worth mentioning that, so I was talking to somebody about this earlier, it's worth mentioning that for performance and using Raft, people usually shard the heck out of it. By that I mean you will have a Raft cluster, you have multiple Raft clusters. And so that could be by directory or it could be by file for this purpose, but you would end up so that you have multiple masters or multiple leaders just for different clusters. And so you end up being able to say, oh, well, you don't have a contention on the read and write because that gets distributed. I am running a single Raft cluster, mainly for simplicity and making it work and going, hey, look, this is kind of neat. So Kepri up here on one node, this is called Vulture 1. It gives me that. Same thing will happen if I do it over here, right? Straightforward enough. I set up, if I do a Kepri that, there's now an entry here that is just foo and bar. And if I were to, now look, there's now foo and it has bar. And on another machine, it's the same thing, go figure. That's it. There's 3 machines. They all have it. And when I said that write right there, that's, I also have a simple web interface to do that. But that's just the write path because I had to implement something to make it work. But the bigger thing is I can shut this down. Now it's going to complain at me because of that. This is still working, right? And the members are there. There are 3 nodes, so it's happy. So the write path still works. So I can do stuff like this where I do, I put foo2 in there. It took it because it still has cluster, still has quorum, even though one of them's down. I can turn this back on. Imagine that just came up. And it'll spew a bunch of stuff. And now, because I did it this way, you'll see an interesting thing. This is still mounted, but that process no longer exists that it's talking to. So now there's an interesting thing where I do this. You get that. So this is a discrepancy of fuse file systems where you end up with the file system doesn't exist anymore, even though it just came back up, because I shut down the program that was running the fuse system. So there are some edge cases here that are a pain. So you do that, kill that, start it again, and now that'll come back. And we end up with, once that comes back up, it's there. And if I were to that, we now have those 2 files. And that server was down at the time of the writing. Right? No. With the content. So that's the basic idea. Yeah, I don't think there was much more because it was really just like, hey, look, use a file system is a thing, 1 slide. I would rewrite this thing in like this Elixir port. It was brutal to work with. I had to add a write path, obviously, so you can just like interact with the file system on the right side to then have it propagate to all other ones. There's a bunch of security stuff, right? It's worth mentioning there's some really good work on the separation of beam instances. On the FreeBSD side, people have gone through, DCH has gone through and done Capsicum, so you can run multiple instances and then have, say, 1 root that needs it for the fuse stuff, let's say, if you need to. But then you can have your other applications not have that permission. Yeah, I'd use RA instead of Kepri, and I would actually use the existing file system. So, yeah, question?
About the multiple beam instances.
Yeah, I will repeat it.
You'll have to repeat.
Yeah.
Is Beam one of those apps where like you can only have 1 per system namespace? Like, is that why Capsicum was required in order to separate them?
Sure. So the question was, is Beam a system where you can only have one instance per namespace, and whether or not that was required because of whether or not how it interacts with Capsicum, very roughly speaking.
Capsicum previously has like the whole namespaces thing that OpenBSD doesn't.
Right. Yeah, so the mention was FreeBSD has Capsicum, OpenBSD doesn't. The Beam can be started multiple times. You can specify an instance name, and those are completely separated. They have different, they're different processes from the OS perspective, and they have different scratch spaces, and they have different identifiers. And so on the FreeBSD side, you can start multiples of them and use Capsicum to do that. On OpenBSD, you'd end up immediately dropping into pledge. And I wrote a small little package that allows you to call pledge from within Elixir, but that applies to the entire instance. So you'd end up having to do that, the entire instance of the Beam, or the stack. So you'd end up starting multiples and doing the same thing. One thing I would like to point out very briefly as I start to wrap up, which is timing not too bad. Any questions or concerns and heckles, and we're done like a little bit early, which is good. I was hoping to actually use the actual file system instead of using Kepri. So Kepri uses, if I were to take a look at my storage right here, so the files that exist in this directory, let's just say, the contents of those files and the metadata about them lives in a directory, and this is just the default naming. You can obviously name it whatever you want, but it lives in a directory that is internal to that system. So I can't go to somewhere and go like, oh, I want to cat, the file or whatever else. Because it's a fused file system, there's nothing saying I couldn't, instead of using Kepri, or even use Kepri and change out the back end, but that's a complicated thing. So probably just use RA or like a Raft cluster and write that to a separate directory. So you end up with two directories on each node, one of which is HA'd and guaranteed consistent, one of which you can do dirty reads from. And if you write to it, it's a problem. But you would end up being able to have that offline. So that's one thing that I wouldn't mind to have done. Yeah, and out of all of this, I would bump the Fuse version. That's on my list of things to do. That's the number one thing, is all of this could have been solved by just bumping the Fuse version, because I wanted a distributed file system. And so I need to buckle up and learn to do that. That's it. Questions, comments, concerns? I'll go over anything else. So crickets. That's really good or really bad? Hopefully bad. Okay, well, thanks. Give you back your time. And you have 20 minutes. I was, yeah, 2:05. So, yeah. Perfect, and there's a little bit of a break. So congratulations. I ran through it quick, but at the same time, there's no point in extending it. I'm going to leave this mic down.
Hi, my name is John Baldwin. I'm here to, well, the title of my talk is Elf Nightmares, GOTS, PLTs, and Relocations, oh my. But hopefully it's actually not quite as scary as the title might indicate. I've been recently doing some work as part of my Cherry project involving working with how linkage works inside of ELF. And so this talk isn't really about the work that I'm doing currently as much as it's kind of the background of some of the work that I'm doing currently and a collection of different things that I've learned like 3 or 4 different times over the years. And so it's just kind of a compendium of various things in this space. So I'll start by kind of defining the problem that we're talking about, like the problem we're trying to solve with this set of topics. Then we'll talk about relocations and what those are, different code generation modes that we use in the compiler and the linker to kind of cooperate. Then we'll introduce something called GOT indirection, that's used for data variables, and then function indirection for function calls using something called a PLT. Then we'll go back and talk a bit more about code generation modes. And if time permitting, we'll talk about these kind of more esoteric topics, things called copy relocations and canonical PLT entries. And then I do have a slide on indirect functions. But I have to warn you that I think that's slide like 45. So I'm just going to see how far we get. I have a timer to stop me with 5 minutes left. So we'll get how far we get, and I'll post the slides, and hopefully they're readable for the things that I don't make it to. So what problem are we kind of talking about? And roughly it's the question of how do we take symbols, which is how we name things in source code with names, like printf is a name that we as a person understand, and how do we map those? So source code refers to these things by strings, because that's what humans refer to them as. But machine code does not think in terms of strings. And I say, like, machine instructions don't think in terms of strings. They think in terms of addresses. And the way things are named in machine code is addresses. And so the problem we're trying to solve is how do we deal with mapping symbols that show up as names, like printf, in the source code and in our brains, and how we kind of map those into the addresses that actually happen at runtime. So I'm going to start off by defining a few terms to give us some shared jargon or lexicon, at least the jargon that I use so you can parse me when I'm talking. So these are my own rough definitions. And if they're wrong, that's okay. It's just my weird language. You can ignore them afterwards. So I'm going to say that a compiler is a program that translates source code from one language to another. And often, in our case, in kind of the world that we operate in, usually you're translating from something into assembly. For example, with C and C++, you're typically having your compiler translate into assembly. So things like Clang and GCC would fall into this. And then assembler is something that takes assembly as input and it generates what I'm going to call an object file as its output. And the object file contains machine code and the initial value of kind of data variables like globals. And object files, as a rule, even across different formats, even though we're going to mostly focus on ELF today, they're generally split into sections, where different sections can contain different types of data. And a general section usually contains the kind of same type of data. So .text tends to only contain machine code, and .data contains variables. Some examples of this are, well, for the GNU world, the assembler as. So GCC will invoke a separate program to do assembly, whereas Clang tends to actually do all this internally. So Clang normally takes your source code, translates it to an assembly internally, but actually ends up outputting an object file directly without kind of being 2 separate tools. So the next kind of step in the process of getting a binary is something called the static linker. At least that's what I'm going to call it. And a static linker takes multiple object files as its input, and it merges the sections from those object files to generate sections in a new linker output file. So for example, we might take all the .text sections and merge them together into a new kind of larger single .text section in a library or a binary. So we can generate executables or shared libraries, and those executables can either be static or dynamic. Some of the linkers, or the static linkers we see in FreeBSD and other BSDs would be LLD from the LVM project or GNU binutils linker BFD. And then another definition, and this is where it might get more, I'll be more opinionated. A runtime loader is a program that takes some kind of dynamic binary and is responsible for loading it into memory and handling initialization of that program so that it can run. In particular, I like to differentiate linker versus loader to actually mean these two different steps of the static linking as the linker and the runtime handling as the loader. But oftentimes, people will also call the loader the dynamic linker or the runtime linker, and the terms get easily conflated. So in FreeBSD, LDElf.so.1 would be our runtime loader. So let's maybe, given those definitions, kind of restate the problem a little bit more. So converting source code into machine code takes several steps, right? We have to compile it into assembly. We then take that assembly and translate that into actual machine code. And then we have a static linker that kind of glues all the things together. So the machine code is generated by the compiler and the assembler. That's how we get into object files. But we don't actually know the final addresses of symbols until we link. So the object files don't have enough information to actually fully define what the addresses are going to be inside of, for example, the instructions. So the way we get around that, or the way we solve that problem, is part of the job of the static linker, in addition to merging things together to build output sections, is it also patches things in the file that it's generating. So we will patch bits of instructions, like individual fields, immediates inside of instructions, or patch data variables. But now we have a new problem, which is how do we describe that patching? We need some way to think about how we're going to manage this patching in a way to describe the operations that we're going to do. So let's talk a little bit more about the simpler case, and kind of the earlier case, because this stuff has also evolved over time, which is linking a static executable. So for object files, they're effectively all kind of created as if they were going to run at address 0. And they have kind of relative addresses of other things defined in the same object file that all assume kind of a base address of 0. So if you have multiple functions, maybe the first one is at address 0, and the next one is at address whatever the first function's size was, type of thing. As a static linker is taking these multiple object files and combining and merging things together, it effectively rearranges the input section. So you might have an object file that has a text and a data, and another object file that has a text and a data. And the linker is going to take the two texts and glue them together, and then take the two datas and glue them together. And so you can have interleaved output compared to what you got on the input side. So the linker is rearranging all these things. And once the linker has done all this, now it actually has the layout of your final output file. And once it knows the layout of all the relative locations of individual functions and individual global variables, now we can actually compute and assign the final addresses of all these symbols. And once we have these addresses, now we're at the point that we have the information that we can actually go apply all these patches to fix up instructions or fix up initial values of data variables to be aware, because now we have the addresses and we can actually finalize it. And for example, define what the address of printf is when we call it. So let's go back and look at our hello world. So the one thing we need to patch in this case is main is going to call printf. And main lives at some place. Here I've kind of arbitrarily said main sort of lives at 0. And printf lives somewhere else in our address space. And there's a branch instruction that's going to call printf from main. And so the thing that we need to patch is we need to make sure that when we actually call printf, we go to the right address. And so once the linker knows the address of printf, it can patch up or fix up the branch instruction to go to the right place. And this can also be true not just for function calls, but some kinds of global variables. Because if a global variable contains an address, it contains a pointer, then we have to patch those up as well. An example of this that Kirk is somewhat perhaps guilty of would be something like telq head initializer, which if you don't know how telq works, the head pointer is null, but the kind of end of the list pointer actually kind of points to the previous element sort of thing. But so it has a nested non-constant pointer inside of it. So that's static linking. But we also, in our world, do a lot of dynamic linking. So kind of how does that become different when we do dynamic linking? So when we're using shared libraries, things get slightly more complicated because some of the addresses for some of our symbols, we don't actually know at static link time. We actually don't find them out until runtime when we've loaded a shared library into our address space at whatever address the kernel has chosen for us when we call mmap. And so those addresses can't be patched by the static linker because the static linker doesn't know what they are. They're not available. Instead, the runtime loader has to handle patching those addresses in some way so that the program can run. And so instead of being patched in the file in particular that ends up on disk, we have to actually patch those every time we create a process and run your program on the in-memory copy. So back to our hello world example, if printf is not actually statically linked into our binary, but our little hello program is linked dynamically and the C library is in a shared library, then only once we actually have loaded the C library into our address space with mmap and figured out what its address is, that's when the runtime loader can patch the call from main to actually call printf. So this brings us to the next kind of topic we're going to talk about, which are relocations. And the first thing I want to kind of say is, why do we call them relocations? Well, the process in the static linker, think about in particular the static linking case, we're rearranging these input sections as I described, and we kind of interleave things. Well, you can think of that for each of those kind of input functions or input variables, at the end of static linking, we've moved them to an alternate address or relocated them to an alternate address. So because we are relocating things around, kind of coping with the fact that we've moved things around, that's where we get the name relocations from. And relocations come in two different flavors. So the first kind are static relocations. And static relocations are kind of a data structure that the compiler and assembler cooperate to generate. Mostly the compiler does it, but they both kind of cooperate. And those describe to the static linker the patches it should do. And those are intended to be generated by the compiler and consumed by the static linker. And those handle things that are defined at link time. Then a second set, rather, of relocations are dynamic relocations. And the purpose of dynamic relocations are also a similar data structure. These are generated by the static linker when it's building an executable or shared library. And they are used by the runtime loader to manage the patching that's done at runtime. So static relocations they come from the compiler, and they're an input to the static linker. And dynamic relocations come out of the static linker and are an input to the runtime loader. And in ELF, both types of relocations, we actually use the same underlying data structure to describe both of them, which makes life somewhat less complicated. Somewhat. So what do relocations look like in ELF? So in ELF, we have a little struct that has a couple of fields. Some of the things that we have are kind of the location that we're going to patch, which you can think of as the target address. Although in ELF, the way it's encoded, it's actually the offset in the file that is going to be patched. We have a type of relocation, which I'll get into more later about how that's used. In some cases, depending on the type, we have the index of a symbol that we can find in a table to find out what its name is, but we have some notion of a symbol that's related to this, probably somehow like the symbol whose address we're going to use for applying the patch. And then we can have an addend, which is an offset applied to whatever address we get from the symbol, or used in some other cases. And the symbol and the addend can be optional. Then in ELF, we actually have two different structures that can describe a relocation. On some architectures, we use a version called elf_rel. And elf_rel doesn't, in the structure, it includes kind of the first three fields, but it doesn't include an addend. Instead, if there is an addend, it's actually stored in the target location. So the way you handle relocations with elf_rel is if it's a type of relocation that needs an addend, you have to go read the addend out of the place you're going to patch, figure out your computation of the value you're going to store, and then you write the final value back to the location, which means you've destroyed the addend. So you only get to do this once. It's not a idempotent. But there's another variation, elf_rel_a, where the addend becomes part of the structure. So the structure gets a little bit bigger, but now the addend is not stored in the target location, it's stored back in the relocation, which means you're not overwriting the addend when you actually do your relocation patching. And typically, older architectures like i386 will use this, and newer architectures like ARM64 and x86, 64, and RISC-V, they all tend to use the version with add-ins, because we learned that maybe it was a bad idea to overwrite your thing sometimes. So I mentioned types earlier, and types are a constant kind of set of numbers you could think that map to operations, and they're architecture dependent, so every architecture defines its own set of types. And the type specifies various properties about what you should do for this relocation. It tells you how you're going to calculate the address that you're going to eventually patch into the target location, and also how to store the result. In many cases, you're patching instructions, and you don't want to just take a 32-bit address, in some cases, and overwrite the whole instruction word. Instead, you might have a 12-bit field at some offset within the instruction word you need to write to. And that's part of what the type encodes is not only the computation you're going to do, but how are you going to take that result and store it? And maybe which part of the address you're going to store. We have an example of that coming up. There are some kind of classes of related relocation types. There's also ones that don't quite fit into these, but some common types of relocations are absolute addresses, and these tend to follow a pattern. They all start with _, but they tend to have ABS at some point in their name. And these tend to take the address of a symbol and add the add-in to it to compute the final address that we're going to store to the target. We also can have relative relocations, which don't get associated with a symbol. They're typically used for things like local private variables. And they're going to take the base address of my executable or shared library, wherever it's been loaded into memory, and use the add-in as an offset relative to the base. So these are basically relative fix-ups to wherever the object file was loaded, or the output file rather. And then you can have PC relative relocations. And in these types of relocations, we're doing a value that's still kind of like an absolute address, but we're going to apply it to something that has the current program counter to hand. And it really wants just an offset relative to the program counter to get to the destination address. So in this case, when we're computing the address we're going to fix up, we take the symbol and its add-in, and then we subtract off the kind of current place that we are, because usually you use this when you're patching an instruction. And the instruction already knows it is using an offset relative to the PC. And these kind of constants are typically, if you look at, I have an example here of a place you can go to see the list of relocations and their kind of the addresses that are computed for RISC-V, and you'll see this kind of annotation used to describe the address calculation formula. So in some cases, you can actually have a single relocation that touches multiple instructions. So in particular, ARX64 and RISC-V are examples of architectures that use multiple instructions to construct an address. x86 doesn't always do this because, for better or for worse, x86 is a variable length instruction architecture. So if you want to load a 32-bit constant, you do. You just kind of make that much more room depending on the opcode you have, and you can patch the full 32-bit or even 64-bit address directly into some location in the instruction. But architectures with a fixed length instruction, like RISC-V and ARX64, well, they have a 32-bit instruction. You can't put 32 bits of address in a 32-bit instruction if you plan to have an opcode somewhere. So you only get to do parts of it. So when you have something like a 32-bit value, you have to split it up into different instructions. And if you do that, every instruction needs its own relocation, because they're going to have to patch multiple things, and so each one gets its own set. So here's an example. We're going to take a very simple C statement. We're going to come back to this in the future. But in RISC-V, if we're going to return an address of something, in this case just some global named foo, when assembled, it becomes a couple of instructions. This first one is a load upper immediate, which takes the high 20 bits as a kind of immediate constant in the instruction, and we'll store it in the register. And then we do an add instruction, which takes as an immediate a 12-bit field that gets the low 12 bits. So these turn into separate relocations for the upper 20 and the low 12. And the static linker has to know that it's kind of getting, every time it computes the same 32-bit address, but it puts different parts of that address at the different locations in each instruction. All right, yeah, I said that, okay. So how do you look at relocations? Because I spend sadly far too much of my life doing this, at least in the last year or so. So there are a couple different ways you can look at relocations if you'd like, because you have nothing else to do. So readelf minus R is one. It just gives you a global dump of all the relocations in a given file, both static and dynamic. For ojdump, you can pass minus R lowercase, and it'll give you only static relocations, and they're actually kind of broken out by section. So you get like a section that has relocations listed, and then all the little relocations for that section and so forth. If you do capital R with ojdump, you can get dynamic relocations instead. And then another neat thing that ojdump has is when you're doing disassembly with -d, if you pass R along with -d, then it adds little annotations in line with each instruction to show any relocations that are applied to that instruction. And then the way that I often end up using this, like for most of the examples later in this talk, is I use a website called Compiler Explorer, which is a pretty nifty tool if you've not heard of it. You get to type in little snippets of C, and then you get to select a version of a compiler. You can pick all sorts of different versions of Clang or GCC or a few others. And you can pick not only different versions, but different architectures, and you can specify the command line flags, and it'll spit out the assembly, or you have options, for example, to actually compile to an object file and dump the disassembly of the object file. So that's often what I actually use to look at relocations, and it's what I'm going to use for most of the examples in this talk. So we're going to go back to the example we had from before. So this is my return foo, but now I've made it actually compilable, add a little more sugar around it. And we're going to compile it with, so with RISC-V, using this version of Clang, turned on O2 so I don't end up with a bunch of assembly instructions that just add clutter. And we'll explain why later, but we're going to do fno-pick. And so we get the load up or immediate instruction I talked about, and we can see we've got this kind of thing around foo. So this says that I'm going to do a special relocation of the high 20 bits, and I have the add instruction with the low bits. So that's the assembly you get out of Clang if you ask for the assembly if we're compiling the return foo. But if on Compiler Explorer, you click on this object, or this little option it has of compile to binary object, then it actually compiles all the way to a .o and feeds that .o, or the object file, into ojdump minus -dr. So it then disassembles the result and shows you the relocations. So now, this load up or immediate instruction, well now instead of having a reference to foo, the instruction just has a value 0, because that's the value that's going to get patched by the static linker. But we can see that we now have this high 20 relocation against symbol foo. So now we've actually turned it into a relocation for real, not just in the assembly. And similarly, now this one looks kind of weird because the way register move is encoded in RISC-V is an add with 0. Right? You just add 0 to the register to the target. So in this case, the disassembler has said, well, you're adding 0, so you really mean to move. But actually, under the covers, it's still an add instruction, just with a 0 constant that this relocation will fix up. All right. So I'm going to switch gears a little bit. And the next topic I want to talk about are different ways in the compiler we can choose to generate code. And we have 3 main kind of modes we can use to generate code. And I'm going to walk through them in a bit of an order. So the first one is something called position-dependent executables, or PDEs. And this is kind of the oldest version. And it's typically would be used for static executables and libraries, but can also be used for dynamic executables, which gets interesting later on. If you wanted to definitely generate this version, you would use -fno-pick with either Clang or GCC to get this type of code generation. Another version are position-independent code, or PIC, which probably many of us have heard of. This is used for shared libraries, and you do -fpic, usually lowercase, some architectures uppercase. Most of them, they don't care which one anymore. I think MIPS is one that cared. We'll talk more about MIPS if we get there. And then lastly, a more recently introduced mode is something called position-independent executable, or PI. That can also, just like PDEs, be used both for executables, static and dynamic, and for static libraries. And the command line flag for it is very similar to PIC. It's just PI. So how did we get 3 different code generation formats? Well, we started off, at least as far as I can tell, with just having static executables and not having dynamic shared libraries. That was a refinement. And so initially we had executables that, when we had virtual memory, were linked to run at a fixed address. So like that's probably what well, I don't know exactly the timeline of BSD that would be, but presumably that's kind of how static executables on at least 4 BSD were. They were on FreeBSD 1 at least. When we added shared libraries, we kind of started off with PDEs as our base and decided, well, how can we add shared libraries to work with the fact that we're used to having these static binaries that are position dependent. So when we do shared libraries, we compile all the things that belong to a shared library with pick. And we link them into a .so instead of a normal kind of binary. But we left executable object files the same. They're still actually PDEs, even though they're dynamically linked. Later, or actually relatively recently, we've actually added the third mode of Pi, kind of largely motivated by ASLR because it wanted the ability to move the executable around in the address space. And it has a couple of implications, if I could speak. There are a couple of implications of switching to Pi. One is you now have to fix up kind of runtime patching of executables the same way you would for shared libraries in Pi, even if they're static, which is part of why FreeBSD doesn't do static Pi binaries currently. And you can kind of think of Pi as a version of pick that we use for shared libraries, but somewhat optimized. It's kind of a middle ground between PDEs and pick. Yep.
FreeBSD 1 had A.out, FreeBSD 3 added ELF, FreeBSD 4 added shared libraries.
We had shared libraries with A.out.
We also had shared libraries with A.out, but it wasn't ELF formatted.
Fair enough. But presumably those, I believe our A.out binaries were still effectively PDE and the libraries were pick.
Yes, they were.
So some of this is, I'm mostly using ELF, but some bits are also applicable to other formats. So what are the things that we had to change when moving from PDE to pick? What's different about compiling things in pick? Well, one thing is that shared libraries can be loaded at arbitrarily different addresses. You don't know at link time what address you're going to be loaded at necessarily. So we can't access symbols directly. We don't know what they are. And we're going to have to fix them up. But one thing that we can use, is we know that even if the shared library is located at a different location and address space at any given time, the relative offset between different things inside the same shared library doesn't change. So if we can get the value, some kind of offset inside our shared library, we can find something else within our shared library because we know it's at a fixed offset from that location. And when we're executing inside a shared library, one location we have that is inside our shared library is the current value of PC. So if we have the current value of PC, we can find something else inside of our self. We may not be able to find necessarily like a direct address, so something in the executable or another shared library, but we can find something inside of our self. So, okay. So global variables and functions that are in a different linked object file, like in an executable or a different shared library, we don't know those at link time, but they are known by the runtime loader. So how are we going to get to things that are not inside our self? So I guess I should back up slightly. That means that if we're in a shared library, we need to get to one of our own global variables. We actually could just take an offset to PC to find it. It's more the case, mostly, that we're in a shared library, we need to get to something else. Or we're in an executable, we need to get to something else, like a value in libc. That's when we have to find some other global. So how are we going to do that? So one approach that we could take is just like the static linker, we could patch instructions. So we could use relocations so that when we load something into memory, we could go patch instructions to change the addresses encoded in instructions. But one downside of this, among a few others, is if we start patching instructions, we can no longer share the physical pages for a shared library across multiple processes, because now we're changing it every time in every separate process. So instead, one of the fun things in computer science, you can always solve many problems. Well, you can solve many problems with indirection. So we use that principle here. And instead what we do is that when we have a variable or a function that we're going to access from somebody else, we access it indirectly. The static linker, as in addition to merging things that come from object files, it also kind of creates out of whole cloth a new array of pointers that's called the global offset table, or the GOT. It says offset table, but they're really addresses, they're really pointers. And anytime we're going to access a foreign kind of variable, the compiler knows we're in pick mode, and if it wants to read some variable, instead of trying to read from the address of that variable instead, it says, well, I'm going to generate a load against a GOT entry to get the pointer, and then I have the pointer to the thing, and I can then read the actual variable using the pointer I got from the GOT. And so this requires changes in how we generate code in the compiler. And then the static linker, when it has, in addition to creating the GOT entries, it also generates dynamic relocations that tell the runtime loader what symbols are associated with each GOT entry, so that when the runtime loader loads a binder and initializes it, it knows what addresses or what pointers to put in all these GOT entries so they point to the right things. So let's walk through an example of that. So I have a little function here named foo, and it's going to reference some variable named x that doesn't live inside the same like executable or shared library. So it's got a GOT, and one of the entries in the GOT is for this variable x. So when we first load this executable into memory or this shared library, the runtime loader is going to walk through and process all the elf relocations it has, which give it instructions on how to patch each GOT entry. So as part of that, we're going to go find, oh, my x, I've done a symbol lookup on x, and it lives over here, some other shared library, we don't care which one, but just somewhere else. And then we'll take the address of x and store it in the GOT. And once we've done that, then now my foo function can access the value of x, because it's going to go read the pointer out of the GOT and dereference the pointer to find the real thing. All right, so now the next little refinement on this. So I mentioned that we can use the GOT to get to foreign symbols, like something that's in another shared library. But it's slightly more complicated than that. So clearly when we have remote symbols, something that lives in some other shared library, we have to use the GOT to get to it, because we have no other way to get to these things that don't live inside of our own shared library. But the compiler doesn't know what symbols might be remote by the time you get turned into an object file. So if you're compiling a given little .c file, for example, inside of libc and you're part of standard I/O, and there's some globals that are part of standard I/O state, it may not be defined in your .c file, but in some other .c file. And as a compiler, you don't know that. You just know I've accessed some symbol. And so I don't know how to get to it, but I have to generate the assembly for the machine code, and I have to decide at that point, am I going to indirect through the GOT? So in practice, and we have another use case, which is sometimes we want the ability, even if a symbol is defined in the same .c file and thus the same .o file, we want the ability to override it. So an example of this is you may want to use a different version of malloc and free inside of libc. You want to use a debugging version of malloc and free with LD preload. Then you need to override all references to malloc and free, including references to malloc and free inside of libc. So instead, what we have in ELF is a notion that some symbols are preemptible and some symbols are not. And a preemptible symbol is any symbol that kind of goes through GOT indirection. Even if it's defined in the same .o file, the same object file, or the same shared library, we're not going to access it directly. We're always going to go through the GOT to find our pointer to access it, because it may point to our version of the symbol, or it may not. So how do we decide which symbols are preemptible? So ELF symbols have a couple different properties. One of them that's somewhat obvious is something called binding, which defines global symbols versus local symbols. So if you do static int whatever inside a .o file, that ends up being a private symbol that's a local symbol that's hidden by its binding. But there's another property called visibility, and that affects how ELF handles global symbols and kind of what rules we decide of if a symbol is preemptible or not. So by default, if you have the default visibility for a global symbol, then we allow other object files and other output files to see that symbol and take references to it. And it's also preemptible. So another output file, like another shared library, could actually define its own version that takes precedence over the version defined in your shared library. There's also a visibility type called hidden. And with hidden symbols, it's still not a local variable, it's global, meaning that it can be shared perhaps across multiple .o files that were used to build up your shared library, but it's not visible outside of the shared library. And this could be useful for things like, if like in standard I/O and libc, you might have some globals that you need to share among all the .c files that make up standard I/O, but you actually don't want the outside world messing with them. You just need to share them inside your library. So hidden visibility lets you do that. And we even have a little wrapper in cdef.h to let you tag symbols as hidden. And then one that's kind of not, I haven't seen used very much, is a visibility type called protected. Protected is kind of a mix of these two. Protected symbols are, other shared libraries can reference protected symbols, but inside your shared library, you always access it directly without going through the GOT. All right. So we talked about using the GOT to access data. Now let's talk about function calls instead of data, because they're yet another wrinkle on top of this. So we could choose to treat functions just like data. We could decide that we're going to have GOT entries for functions, and anytime you're going to call a function, you go read the entry out of the GOT in your codegen, and then you branch to it. So you do a load and then a branch. But ELF doesn't do that for a couple of reasons. One reason is that many libraries might have a lot of potential remote functions we might want to call that are associated with a lot of GOT entries. If you directly have the compiler always assume it's going to kind of read from the GOT directly and call the function, then every time you would relocate one of these shared libraries, you have to go and populate all those GOT entries. So in particular, think about libc. Libc has references to all sorts of things. But a given program like ls may only use a few of the functions from libc and not all the internal bits that go and call off DNS resolving and stuff like that. So you might spend a lot of time applying relocations for GOT entries that you're never going to call. The other thing that we're going to get into is it turns out static functions compiled with PDE that are dynamic also need a way to call remote functions. And they're already defined to use simple branch instructions. So instead, we make a different choice in ELF. We use something called a procedure linkage table, or PLT, as a way to handle remote function calls. And so what we do with the PLT is for every preemptible function that a given shared library or executable might call, we create a special little stub function, usually only a couple of instructions or like 3 or 4 instructions long, or a thunk in this PLT. And it's an array of these stubs. And every stub function does only a couple of things. It has associated with an entry in a new GOT. We actually have a separate GOT called the PLT GOT, which is different than the other GOT. So we have 2 GOTs now. And the stub function reads a pointer out of the PLT GOT and branches to that. And then every entry in the PLT is associated with the dynamic relocation. Usually it's named a jump slot. And the symbol for that relocation is the name of the function that's associated with this stub. And the target address for the jump slot is to fix up the GOT entry to point to the function we're trying to call. So it turns out, I guess the next way to describe part of PLTs is to solve that first problem we mentioned of not spending a bunch of time fixing up GOT entries, we only fix up PLT GOT entries on the fly the first time a function is called. So to avoid all that overhead, we only do them the first time. So the first entry in the PLT is actually kind of special. It's usually a bit longer. It's not just 2 or 3 instructions. And it's a special kind of thunk called PLT0. And what PLT0 does is PLT0 reads a couple of entries from your PLT GOT, usually at the very beginning. One is a function pointer, and one is some kind of opaque data pointer. And the way the PLT thunks work, the normal stubs, when they're configured at startup, they don't jump directly to the target function. Instead, what they do is they actually jump to this PLT0 stub, and they have, as part of the way PLT stubs are defined, they pass along, usually in some register, the index of the given PLT stub and the whole PLT. So you kind of know which PLT stub you are. Some architectures, you can use the return address to figure this out. On x86, it's actually this little instruction in the bottom of the PLT stub that puts a value in a register. But effectively, we can figure out, when we get into PLT0, which PLT stub you're from. And we're going to, all right. Oh, that's what I'm saying here. Sorry, my brain went further ahead of my slides. So we have the index of the PLT entry, and we have that to hand when we get inside of PLT 0. So this means when PLT 0 runs, it reads these two pointers, and it calls the pointer, the function pointer, passing this data pointer, but also, in some other register, this index. So the function pointer that we're calling gets two things as its input. It gets some kind of data pointer that came from the GOT, and it gets the index to say which PLT stub actually is trying to resolve a symbol. So what the runtime loader does, on the kind of backside of this, is the runtime loader initializes those two entries in the PLT GOT to point to a special function that it's going to use to handle resolving PLT symbols, and it stores a data pointer that describes which shared object is trying to make the call. In the case of FreeBSD, this function is usually written in assembly. It's called RTLD bind _ start, and it has a little bit in assembly that eventually calls RTLD bind in C. And the data pointer points to the obj entry structure, which is a structure that FreeBSD's runtime loader uses to describe each shared library. So we get the pointer to this data structure and the C function that this calls, and we also get the PLT index inside of the RTLD bind function. And we can use that. So when we call this, it takes that PLT index, and to figure out from this obj entry, we know which PLT we're looking at. We can use the index to find the relocation table, find the relocation inside that relocation table, and that tells us what symbol we're looking for and which GOT entry we're going to patch. So we apply the relocation, it fixes up the GOT entry, but then we have one last problem, which is the very first time we were called to jump to like printf or whatever target we were going to. Well, we can't return to the caller and try to have it call again. It's already called us. So when this assembly function returns, it doesn't return to whoever called it. It actually returns by jumping to the function that we're trying to call the very first time. All right, so I have a picture of this that hopefully is better than the wall of text. All right. So we have, in this case, a little dynamic binary. It's going to call printf twice. You'll see why in a second. And we're going to rely on the compiler to not cheat and turn this into puts or combine into a single call, which compilers will do to you because they're our adversary many times. But just pretend like it actually thinks what you think it does. So the output that we would get once we've compiled this and we've linked this into a dynamic binary is we've got a main function, and we have a PLT that has this PLT 0 stub at the beginning, and it has an entry for printf. Which in assembly we tend to call this like printf at PLT. It's how we annotate and distinguish the real printf from the PLT func for printf. And then we've got our PLT GOT, which has got a couple of entries, right? Just like a normal GOT, this is an array of pointers. So when our runtime loader starts up, first it's going, well, right, but back up before that. The way this is kind of linked at static link time is that the branch in main that's going to call printf, every time it calls printf, it jumps to this printf at PLT. That's going to read the address of printf from this third slot. And that's kind of the way we're finally linked from the static linker. So now let's actually start executing and see what the runtime loader does. So the runtime loader, it maps the binary, the kernel maps the binary actually, and it maps this. And in the runtime loader, we have our TLD bind start over here. And as we're relocating this object, we allocate a data structure. And for the main executable, it's called obj main, if you go dig around in the source code to the runtime loader. And the runtime loader is going to configure these first two entries in the PLT GOT. We have the code pointer that points to RTLD bind start, and we have that opaque data pointer that points to obj main. And the way we process the relocations initially for the PLT GOT, we've changed effectively this third PLT entry actually to jump to PLT 0. And it turns out that's cheaper than the normal relocation we would have to do, even though we have to do a little bit of work. And then, because this binary said it needed libc, we go ahead and map that in, and it has a printf function. Now we're ready to start executing. So what happens the first time we call printf? Well, the first time we call printf, we're going to jump into the PLT stub. Yeah, I should back up a little bit. All right, now let's call printf. So we're going to, the first time we call printf, we're going to follow jumping to the direct branch instruction, going to the PLT. Then the PLT stub is going to read from here a pointer that points to here. So it'll jump into here. And that's actually going to go call this function with passing this data variable And the runtime loader uses it to figure out this is the thing we're trying to change. So then the runtime loader is going to rewrite it to point to here. And then it's going to return. When it returns, it's actually going to call this function. The second time we call the function, and we call branch, well, the second time we actually branch to here just like we did before, but now the value we read from the GOT is the function we directly call to it without taking a detour through the runtime loader. All right, so where am I at? Because now I'm out of time. Okay. All right, well, this is as good a place to pause as any. Well, we'll get to some of the fun stuff. So do you have questions? Do you want me to try to go further into the break?
Well, perfectly clear.
Well, it wasn't perfectly clear to me the first few times I tried to learn this. Does anybody have any questions, or do you want me to keep going, or what would you like? All right. So we'll keep going for a few more minutes. So let's revisit this notion of PDE and PIC and PI and go a little more fancy. So I'm going to have the same little snippet of code. We're going to use Compiler Explorer. And we're going to do a couple of things in this function. We're going to take the address of a global, and we're going to call a function, and both of these are remote. And we're going to look at what assembly we get in each different mode and kind of what relocations we get. And in this case, we're going to stick with x86. We're using GCC, and we're doing, to start with PDE, we're doing fno-pic. So we get a couple of things. We have some kind of boilerplate around managing the stack pointer. But we're going to read, the $x here means we're taking the absolute value of x, kind of encoded as an immediate instruction, and storing it in this register, which gets passed as the first argument. And then we're going to call bar. And the way both of these are encoded, this one is an absolute address, and this is a PC relative branch, but it kind of hard codes the offset that it's going to jump to bar. So what if we compile this as a shared library instead as PIC? Well, now we see the code's changed a little bit. Like this part's the same, these last 4 bits are the same, but these 2 instructions are a little different. Instead of $x, now we're doing a read from a memory location, and the memory location is PC relative. So we're using the PC to find the location of our GOT and reading the address of the value of x from the GOT. And then that's a pointer that in x86 we can kind of read from the pointer directly to, or no, we're getting the address. Never mind, we're just reading the GOT entry directly. So this is reading from the GOT to get the pointer and storing it in the register. And then when we call bar, now we're actually saying we're explicitly going to go through the PLT stub version for bar instead of directly calling the function. So that's the differences we get with PIC. So then, what if we're not doing a static binary, which was the first version I showed of the PDE? What if we're doing a dynamic binary? Well, it turns out the code generation is the same, because PDE is PDE. It doesn't really care if you're static or dynamic. So what if x doesn't live inside my binary? And what if bar is also not inside my binary? It's in a shared library, right? Because the code gen is assumed that it has the address. So with dynamic executables, we have a couple of tricky cases, some harder than others. The first one, the easy one, is how do we handle branches by calling bar from a dynamic executable that's compiled as PDE? And the answer to that was, well, we just use our good old friend, the PLT stub. It's actually what my lazy PLT example did. The linker can add a GOT PLT and a PLT stub, and it can rewrite that branch instruction not to try to call bar, but to call a PLT stub. And that's all good. We're fine and dandy. But the data variable case is a little bit more of a pain in the butt. So how are we going to handle the fact that in my executable at static link time, I have to compute a fixed address to store an instruction for a variable that lives in a shared library, when I won't know what the address of that variable is until I load the binary at runtime? And here we use this thing called copy relocations. And if you don't shudder, it means you haven't worked with copy relocations. And the way a copy relocation works is a static linker reserves space in the BSS of the executable for a new version of x. We're going to call x prime, a copy of x. And at runtime, when the runtime loader loads the binary, it finds the real value of x from the shared library, copies that value over into x prime, and then for all the future lookups, anytime anything, either the shared library or a binary tries to find x, instead we redirect it over to x prime. So what does that look like in practice? So here we have our little binary with foo, and it's going to reference x. And the static linker has created this x prime as a place in the BSS. And then we have a shared library that actually has the real value of x that we, in theory, should be using. And because in pick mode, we know these type of shenanigans can occur. This is part of why we have marked x as a preemptible symbol. Anytime the shared library tries to access x, it actually goes through a God entry to get there. So we have a God entry that tells us the address of x, even for use in the shared library. So as the runtime loader starts up, it's going to copy the value of x when it does a symbol resolution and finds it lives in the shared library over into x prime. And then it's going to store a pointer over in the God entry for the shared library, not to point to the shared library where it really lives, but now to live in this alternate copy over in the executable called x prime. And we're going to just pretend like x doesn't exist at this point. It's just wasted memory. That, you know, la, 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 don't believe the symbol table. It does not exist. So that's kind of yucky, especially, it's one thing if this is an int, but imagine more complex data structures. This gets really wonky, and things like alignment and it can get messy. It will resolve and call the real function eventually. So that all seems fine. But C has this little requirement, which is that when you take a pointer to the same symbol, all the pointers to the same symbol need to compare equal. So if the executable is going to get the address of the PLT takes a pointer, everything else, including any shared libraries like libc in the process, also have to get the address of the PLT stub where they take a function pointer to fclose instead of the pointer to fclose. All right, so now we have a picture of that. So you can think of this as kind of like copy relocations for function pointers. So here we've got our executable, and it has the foo function. It's going to call fclose. And, well, yes. So even though we don't call fclose, we need a function pointer. So we make sure that we're going to create a PLT stub, even though it doesn't get used, just so that we have this God entry that can be the function pointer. Does that make sense? Is it terrifying? And the PLT stub is going to read that entry out of the GOT. That's kind of like before. And then we have libc. And because it's pick, it knows that it has a God entry for fclose because maybe it's been LD preloaded or who knows. So when the runtime loader processes this and it finds the relocation for the God entry for fclose and libc, it's responsible for sending that not to fclose and libc as it normally would, but instead to point to the PLT stub. Which means that any time that libc wants to call fclose via a function pointer, it uses the function pointer from the GOT to jump to the executable, to go to the PLT stub, to go into the runtime loader, to then fix this up to point to the real fclose, and then jump back into itself. Yeah, that's all. I guess I stepped ahead of myself a little bit. Yeah, see? All right. So I was going to talk about pi. I don't have time to talk about pi. I have many more things, but I need to get to at least the slides at the ends. All right, you can read about that one. All right, I will do this slide, just because MIPS always needs a good kicking. So what about MIPS? So MIPS is a special snowflake architecture in my mind. I think it suffered from being the first to do some of these things. So with MIPS, we don't have dynamic elf relocations to figure out how we're going to patch our GOT. Instead, we have these kind of implicit rules that we have a single GOT, not a separate PLT GOT, and then we use these tags in the dynamic to split the GOT up into separate regions. We have a region of local symbols. It's kind of like relative relocations, and we always know it's a relative relocation. We just add the base address to whatever's in the GOT. That's it. Then we have a second region called global, and global is split into two pieces. The first part of global are global variables, and the last part of global are PLT stubs. There's a couple of DLT tags that tell us, A, for the global variables, and actually all of them, there has to be a contiguous range of indices in the symbol table that start at this index in the symbol table to tell us what all the symbols are. And the PLT stubs use some portion at the end. We have this tag in the dynamic that tells us when to stop doing global variables, and presumably everything after that will be fixed up lazily. Then the index that comes into the runtime loader from when we're doing the lazy PLT resolution is actually the index into the symbol table. and we take that index and we subtract the starting point of the kind of global region symbol table to get an index into the GOT, except that it's an index relative to this region, so we have to add the base part of that region, and that tells us what index in the GOT we're actually fixing up. More reasons I dislike MIPS. But in particular, because you can't, imagine if you wanted to do some other calculation for some other reason, like Cherry. All this stuff is hard-coded, and it becomes just a giant pain in the butt. The fact that we now have relocations where we can configure how we're going to do behavior and figure out which slot to do it and not have it kind of all this hard-coded gunk, life is better on everyone but MIPS. So when people say, why did you not like having MIPS in the tree? This is one of the reasons I didn't like having MIPS in the tree. All right, this is my last slide. Y'all can read that stuff. Thank you. If you have questions, you can ask. It's the only book I know of.
So nothing current.
And this doesn't cover, I wanted to talk about TLS in my talk, and even though I have another 10 slides I didn't get to, I didn't even try to write the slides for TLS. And I don't have a link to that, but like this book is before TLS. It's kind of interesting that it does talk about Windows, so you can learn a bit about how linking works in Windows in the late 90s, because I read this when I graduated from college. So you can imagine things might have changed in 25 years. But there might be other books. I'm not aware of one.
Some did publish in our book. I have a copy. You may not have it.
Okay.
It's a good read, but because the publishing is old.
That's good to know. Thanks. Any others? Okay, you should get to your next talk while you still can. Sure.
One of you. Okay. Well, you should be in some other place because you've already heard the talk. All right. So first of all, I want to just talk a little bit about my role here. I'm sort of the grand old man that talks about the good old days. More to the point, I am not playing Linus Torvalds and trying to be in charge of everything for the entire lifetime of me. I did that for 10 years in the 70s or in the 80s and into the early 90s, and then that 10 years was enough. And I'm very happy to see that we have had continued turnover of leadership and new people coming in place, and you're not stuck with my view of exactly how things should be done. Okay, so that's what I'm doing. I'm going to talk about some history, in this case of the BSD daemon. Now, this was actually an interesting project that I got roped into doing for the Developers Summit, and I kind of did it at the last minute. And so when I got there, I had sort of a collection of slides that I hadn't really looked at, no concept really of what I was going to say, and a big pile of T-shirts. And so if you watch the video of it, you know, there's George is there and he's holding up shirts, and I go on rambles. So it was an hour and a half, and when I finally got rid of all the crap in it, it turned into a 40-minute video. But hopefully this one will be a little more focused because I now have 41 slides and I don't have lots of shirts. And so hopefully it'll be a little more coherent this time. One of the things that was very interesting about putting this talk together was that I had to go through boxes and boxes and boxes of shirts. I've been described as the Imelda Marcos of T-shirts. I have, well, at one time about 1,000 of them. And so I can be wearing a shirt that, you know, I'm wearing it for maybe the second time ever, and even though it's like a 30-year-old shirt. But the other thing is that pictures used to be done with these things called film, and they got printed on little pieces of paper. And so my digital photography only goes back to around the beginning of the 00s, and everything before that is in boxes and boxes and boxes of pictures. And so I ended up going through many of these boxes of pictures looking for things that were some of the earlier bits of the history. And one of the pictures that I came across, I just couldn't resist putting in here, which is the next slide. But before I show you that slide, what I want to tell you is where this picture came from. I was at Berkeley, and at the time we were just getting ready to release, or had just released BSD, which later became known as 1BSD. The main thing that was in that was the Pascal system, compiler and interpreter and debugging and all that. And so I decided, well, you know, people are using this, and so I could put together a tutorial about it. And so I submitted the thing to do a tutorial, and they accepted it. And then they said, oh, well, you need to get a picture sent in. Well, I didn't really have a picture, and so I sent some random little picture, and they go, no, no, you need to go to like a professional photographer and get your picture taken. And so I did that, and I sent them this picture. They got one look at this picture, and they said, you're too young. Nobody's going to sign up for your tutorial. And they were right. 5 people signed up, and 4 of them actually showed up for that tutorial. But the good news is that I've, since that time, improved the number of people that come to attend. And I figured out, somewhere in the order of 10,000 students at this point. The other benefit is that this guy named Eric Allman saw this picture, and well, we had sort of a 3-year on and off thing, but eventually decided to move in together. And last month celebrated our 46th anniversary, so that kind of worked out. Okay, so let's start with the name of the daemon. The daemon is unnamed. He is the BSD daemon. But people can't cope with the idea that he doesn't have a name, so they kept coming up with names. And one of the names they came up with was the name of the person that used to harass me in high school. And it's like, all right, Chuck is not going to be his name. That's just not happening. So we finally, Beastie seemed to sort of settle in as the right name to use. And of course, there was the whole thing of, you know, this is a demon, and it's like, it's not a demon, D-E-M-O-N. That's an evil spirit. Rather, it's a daemon, which is a deified being, half man, half God. And so, anytime people start talking about the devil or the demon, you need to explain this to them. All right. So let's start sort of really at the beginning. And sort of the first place where we get a notion of the demon is this picture here. It was commissioned by someone named Mike O'Brien, who was big in the early Unix days. And he had this person, Phil Figlio, was his roommate. And the apartment they rented had a safe. And they kept their valuables in that safe. At some point, Mike O'Brien moved out. And then, maybe a year or so later, Phil was moving out. And he realized his valuables were in the safe, but he didn't know what the combination to the safe was. And furthermore, Mike had no idea what it was either. But Mike had gotten actually a credential to be a locksmith, and so he had access to books that explained how to crack safes, and it was a fairly crappy safe. So in about 15 minutes, he managed to get the safe open, and the compensation that he got was Phil, who was an artist, drew this picture. And this is, of course, a PDP-11, and there's the pipes, and there's dev null over here. And then there's the little demons that are running around, and they're the processes that run in the background to do stuff on your behalf. And you'll notice here, first of all, that it's signed by Figlio, which I have this thing about where artists' names get removed from things when they get put on various posters and so on. All right, so that's the very first picture that we have. The first sort of use of that beyond just the poster, well, actually, Mike O'Brien had some shirts made up with that image on it. But the sort of most widely publicized was when Usenix, for the 10th anniversary, had this on the T-shirt. And you'll notice here that somehow the artist's name has disappeared off the picture, or off the shirt. So the time rolls on, and now we're getting ready to print the manuals for BSD, and we wanted some kind of cover art. And so Sam Leffler, who was one of the early people working on BSD, eventually had left and had gone to Lucasfilm. Lucas at this point was doing the Star Wars movies. He'd done the very first one. It had been wildly successful. All the special effects were done with blue screen and models and so on. And he wanted to try and bring some computer technology into making that an easier thing to do. And so Sam was in the Lucasfilm computer division. He was there, and the early stuff they were doing was really just scanning films and being able to add a few artifacts and so on. It was nowhere near where we are today. But one of the other things that happened there was that John Lasseter, who was an artist, a lead animator at Walt Disney, was on a sabbatical. So in the old days of cartoons at Disney, there was the sort of 3 levels of hierarchy. Everything was all hand-drawn. And so the lead animator would draw a cell. And then they'd do the next cell that was 1 second later in the movie. And then what would happen is that the second level artists were called the in-betweeners. And they would fill in the 29 frames between those two. And then finally, the lowest level people were the colorizers. And so they'd be filling in all the little bits of color. And they were given a little bit of artistic stuff, the tail. They could get to draw the tail and make it go woo, or something exciting like that. At any rate, the lead animators, because they were so important at Disney, were treated sort of like university professors. And so every 5 years, they would get a 6-month sabbatical where they could go off and recharge their batteries. So John Lasseter took his sabbatical at Lucasfilm. And of course, the thing that he was interested in was this notion of using computers to help with the animation process. And so one of the things that they were trying to do at Lucasfilm was to build an animator's workstation. Well, they had people that knew massive amounts about graphics and computer graphics and all that, but they didn't have the clue as to how someone that was actually an animator, what kind of user interface they wanted. And so to them, having an actual animator come and spend 6 months there and go, that's ridiculous, you don't do it like that, you know, I need this, and I need to be able to do that, and I want this to move, and so on and so forth. And so it was great, you know. They came up with something which is actually the basis for what's used today. RenderMan also came out of that project, believe it or not. So the upshot was that Sam was there. He had just left Berkeley. He knew we needed cover for the manual. And so he said to John, oh, John, could you just draw us up a picture? And he showed him the previous thing, you know, the little demon guys here. And so I don't have the picture with me like I did down in the previous talk, but this is literally a piece of sort of cream-colored cardboard that he pulled out of the wastebasket. And there was a tray that had chalk on it, and he just, in about, Sam said, 20 minutes maybe, drew this up. And you notice that it has a sort of Disney-esque, sort of the big eyes and the other things you would kind of associate with Disney. I don't say that too loudly because then Disney might have a fit, but that's kind of where this came from. And then, there's the glowing orb, which says Unix on it. And you can see that it's throwing a shadow, and down underneath the tail, which is a little hard to see in this picture, but he signed it right underneath the tail there. Okay, so this, of course, then got used on the manuals. Voila. So these were published by Usenix. And remember, in those days, Unix was licensed, and you had to buy a license. If you were a university, you got it for not much money, and it was a perpetual license, and then you could have it on as many machines as you wanted, blah, blah, blah. Because in those days, AT&T was not allowed to sell computer stuff. There was the dissent decree where IBM sold computers and had nothing to do with telephones, and the opposite for AT&T. So they could do stuff internally, but they could not sell anything having to do with computers. So, great. Let it go out into the world. I mean, they keep a license on it. We know who's doing stuff, but that was about the extent of it. But that meant that you couldn't just go to a publisher and have them publish this stuff which was unlicensed material. But Usenix had a license, and so they could print the manuals and make sure that they only sent the manuals out to people that had licenses. Okay, so we roll on here. This daemon got used in a whole bunch of ways. And so the first one was that it got colorized. Now, I want you to just notice here, he has no shoes on. Okay. He's naked. I mean, let's just be honest here. Okay, but for some reason, when they went to do this, they felt he needed shoes. He didn't need any other clothes, but he had to have shoes. Okay, so this is the first place where you start seeing him wearing sneakers. And of course, the BSD, Unix, etc. Okay, so I got a request from St. Olaf College in Minnesota saying, oh, we'd like to use him in our logo for our computer science department. And I early on came up with this thing of, well, I want to keep control of the copyright, of the licensing, but I want people to be able to do reasonable stuff with it. So the royalty that I collect is that you have to send me 2 t-shirts, one in medium, one in large, because I fit medium and Eric fits large. And so that's how I have this ever-growing collection of t-shirts, which mostly involve things having a daemon on it. And there's certain rules, like you can't have the daemon fucking tux your, those kinds of nasty bits. Okay. It even got picked up by the Bay Lisa. The Lisa is the large installed system administrators. And in this particular case, you can see he's working with this thing called Ethernet. In the old days, that was actually like a wire, and you know. And then another one of my favorite ones, the Love, Peace, and RDist. RDist was sort of a predecessor of rsync. And so, I'm not quite sure. These were the people that were, trying to promote RDist as a thing. I mean, it was open source software. They weren't getting any money for it. But nevertheless, they wanted to have t-shirts, so I got 2 of those. All right, so now it's time to move on to the second version of the John Lasseter daemon. And this came about because we needed we wanted to have it for our textbook. This was the very first textbook that we did about BSD, design and implementation of the 3BSD operating system. And in this particular case, of course, I wanted John Lasseter to do it. Sam was still at Lucasfilm and still had some contact with John, who wasn't there at that point, but got in touch with John, and oh, I know where it was. John had come up to visit. That's right. He'd come up to visit because he wanted to see the next iteration of the animator's workstation and give more feedback. And at that point, I think he was trying to get Disney to actually buy a couple of them, because this is the one where this was just a blue piece of cardboard that he pulled out, and some more crayons or chalk. No, this is actually chalk also. And again, you can see underneath his tail there, it says John Lasseter 88. And this one, I wanted to, make it clear that, it was a work for hire. So it was a work for hire, and I paid him $1,000 for it. And, got the paperwork because Addison Wesley wasn't going to let me, put something on the cover of a book that I didn't have the rights to do that with. And in fact, I had said, well, we've got this BSD daemon we want to put on the cover, and I don't think they really, connected what that was, because when I actually sent it to them, or print a picture of it, they're like, oh, we can't possibly put this on a book. This is a serious textbook. And we were first-time authors, and usually first-time authors get no say about anything. But someone whispered in my ear that, if you really insist on it, they will eventually cave. And so we're like, no, really, we want it on there. And see, it was on the cover of the manuals, and everyone associates it with this. It'll help with sales, and blah, blah, blah. And so they eventually did relent and put it on the book. Now, you'll first of all notice that the glowing orb is missing, because the glowing orb was going to be there, but they didn't want to put Unix in it, because even though it said 4.3 BSD Unix operating system, they didn't want to put it on the orb. So, but the shadow is still coming down. But none of them knew who John Lasseter was. So of course, John Lasseter does not appear underneath his tail in this particular instance. Okay, so that book then went on to sell 50,000 copies, and suddenly we looked brilliant. Okay, so time continues rolling forward. Oh yeah, there's many other instances. Somebody actually did a stitching pattern for the daemon. This is 20,000 stitches, and you may have seen, actually Margot was wearing a variant of this earlier today.
The shoes are blue now.
What?
The shoes are blue now.
Yes, yeah. The problem was that if you only get like 4 thread colors. And so if we'd want to do red, then when you did the red down into the sneakers, they didn't stand out enough. And so they went back and changed the, used one of the blue colors for the shoes. Yeah, some compromises in certain technologies here. Okay. It also, at that point, I guess it was the early 90s, I did a trip around Australia. They have a meeting in September, which is a single countrywide meeting. This was their equivalent of Usenix. And then in the February, March, April timeframe, each state has their own conference. And there's 7 states plus the Capital Territory. And so what they did is they had them on a 1-week headway. So I spent 2 months traveling to every capital city in Australia and giving a lecture and so on. So they made this commemorative shirt of McCusick doing Oz. And I got more than 2 copies of this one. All right, and then of course there's the, we continue to have the, let's have some fun. So DOS was the big thing to poke fun at, so we're poking fun at it. And then of course when FreeBSD got released, they wanted to have a t-shirt. And so here I did a special version of it where the daemon is free. And note that John Laster's signature is on this picture. But of course, FreeBSD wouldn't really fit in there, so we just stuck that up at the top. It wouldn't fit in the orb. And of course, the very well-known version that was done for the Walnut Creek CD-ROM, where the daemon is walking out. I'm a collector, so I have every version of FreeBSD DVD that was released. So I went through, and 2.1 was the first one that had this picture on it. And it continued on there for several years, several releases. Okay, so time rolls forward. And now it's time for us to do the next version of the book. And we had done the 4.4 book, or we're doing the 4.4 book. And so I wanted a new version of the daemon. So at this point, Lucasfilm's computer division, well, the Star Wars movies, the first trilogy had come out, and there had been a long gap. And so this huge influx of money that had been coming into Lucasfilm started to dwindle. And so he had a whole slew of projects that he'd started, and he couldn't really continue to support all those projects. And so the computer division had done what he wanted them to do, and so they got spun out and into a thing called Sprocket Systems, which eventually became Pixar. And so, as I'd said, John Laster was really excited about Animator's Workstation and using computers more for doing cartoons. And when he'd gone back to Disney, they were just like, no, we're not doing that. That's just cheap. We believe in the true way that we've been doing it for 50 years and blah, blah, blah. And so John got rather discouraged by this and left Disney and came to Pixar, because Pixar was all about doing things with computer animation. And early on, they didn't really have the money to do a feature-length film, but they did a lot of advertising, 1-minute ads that would run on TV and things like that. And so what had happened is that they had, Steve Jobs bought Pixar, and Steve Jobs went to Disney and said, look, we want you to fund doing a feature-length film. And there wasn't really any other place they could talk to, and Steve Jobs wasn't rich enough at that point to do it himself. And so the upshot was that Disney got this incredible contract, which was, all right, we're going to pay for it, and you're going to get complete artistic control. But we are going to get 90% of the revenue that comes from showing it. And Pixar goes, oh, you know, well, all right, just at least let us get the spin-offs for, you know, any merchandise. Because at that time, merchandise associated with films was nothing, zero. It just didn't happen. But, you know, they were doing Toy Story. There's some really obvious merchandising that can go on here. And of course there was, you know, I mean, they went to the people that they were using the toys of and said, you know, we want to do a joint thing with you where, you know, we'll get some of the royalty from you selling these toys. And a bunch of the toy companies were like, nah, we're not doing that. But a select set of them did, and boy, did they ever look smart, because the merchandising brought in twice as much money as the receipts from showing the movie. And boy, was Disney surprised. All right, but I digress. So I went to John. They had just, well, they were getting going on Toy Story, and he was like the lead guy for Toy Story. And so he was, let's just say, a little bit busy. But one of the things I learned was that, you know, making friends with his secretary was a really good plan. And so I would go in, and I mean, he'd agreed to do it, but, you know, then there's the agreeing and then getting it done. And so I went, you know, I'd go in and say hi, and I'd bring flowers or chocolates or, you know, some little thing. And he's like, well, he says he doesn't really know what you want. I said, well, I want him to be kind of animated, you know, instead of just sort of standing there, you know, let's have him chase the glowing orb. And so she said, all right, I'll give him that. And so about a week later, I got a bunch of sketches from John. This is being the one that I sort of like the best. And I said, yeah, something like that. And so then time really started to, you know, go on and on and on. And the problem was we were getting like to the point where the book was going to go into production, and we didn't have the picture yet. And they're like, look, if you don't have the picture by this date, you know, we're doing something else for the cover, because, you know, we're just not going to wait that long. So I got a little more desperate, and, you know, I think I sort of upped it, you know, instead of just like some flowers, you know, it was like a really nice box of See's chocolate. Anyway, the upshot was that I get a call from her and said, okay, he's done it. And I went in to pick it up, and she said, you know, he'd said, all right, I put it on his schedule for this particular day, and I had the paper there, and I had all his pens, and they were all inked and lined up. And he said, he sat down, and he just, you know, he had the picture of the little sketch next to him, and he kind of sat there for about 5 minutes, and it didn't move. And she says, everything okay? Is something missing? And he goes, I haven't drawn an animation cell in 8 years. I don't know if I can still do it. And then she said, he picked up the black pen, picked up the other, something like 15 minutes this got done in. And of course, signed underneath, John Laster, 94. Okay, so armed with the picture, I sent it off to the publisher with days to spare. And of course, it became the cover of this book. Now, I want you to go back and notice here, he's chasing the orb. You know, he's starting to go after it. And so, of course, the orb is trying to take off because it doesn't want to get stabbed. Well, they looked at this and they go, that looks much too much like a sperm cell. So you'll notice when we get on the book, somehow the glowing orb has just disappeared. He's just running for a good time, I guess. But you will notice that John Laster's name, who's now, by the time the book came out, associated with this movie called Toy Story, which everybody's talking about. So suddenly the marketing people think it's okay to leave the John Laster's name on there. If you look inside on the copyright page in all of the books, we always credit him with the cover. But this is the first time now it finally appears on the book cover itself. And he also appears on the spine, and miraculously the glowing orb is missing on that one as well. There was an interesting story here. Actually, it was the previous book. And we get this distressed call from Addison Wesley. And apparently the people that deal with books for schools in Oklahoma have decided that this book is going to be banned because it's got a devil on the cover. And they don't want those high school kids to be exposed to the devil. So, they want us to write a letter and say, no, really, this is a technical book and blah, blah, blah. And Keith Bostick looks at me and he goes, don't do that. I mean, how many people in Oklahoma are going to buy that book? Just put a big banner across it that says, banned in Oklahoma. You'll sell a lot more copies. They didn't see the humor in it. Okay. So again, there was a stitch pattern. This was actually the one that Margot was wearing this morning. This one was it's actually a bigger stitch pattern, and it had 27,000 stitches in it. But it turned out that the MS-DOS machines that run the stitchers, for whatever reason, can't deal with more than about 24,000 stitches. So I had to go back to the artist and say, could you please remove 3,000 stitches? Who knew? Okay. Well, time went on, and so the AT&T started, Berkeley started working on trying to get a redistributable, un-AT&T licensed version of BSD out. And initially, what had happened was that the consent decree had ended. So now AT&T was allowed to sell computers and computer systems. And so now they're starting to sell Unix. And so the price jumped from like $20,000 to $250,000. And it was for one machine, and you had to pay extra for any additional machines, and it was limited to 10 people that were allowed to have access to it, and you paid extra for more people, and blah, blah, blah. Well, there were a lot of people in those days. Well, let's go back. The IBM PC was very limited both in its compute and memory. And so if you wanted to have, let's say, TCP/IP on it, there really just wasn't room to put TCP/IP into the operating system. So the way you did it was on the board that just looked like a peripheral to the PC. And so they needed to have the TCP/IP in that. And so they came to us and said, look, can you just at least give us TCP/IP code? And so we talked to the Berkeley lawyers and back and forth. But eventually we did what we called the networking release 1. And that was the TCP code in the kernel and the socket level stuff and all of the great utilities like rlogin and a few other things that should never have gotten out but did. At any rate, RSH, yes. The upshot was that was very successful. And so we decided that we would try and get more. Well, Keith Bostick decided we would try and get more. And Mike and I, who were sort of dealing with the kernel for the most part, and Keith was, he was doing everything. I mean, he was dealing with all the user level stuff, all the comments that came in, so phone support and everything. But anyway, we're like, well, we don't really know how to do the kernel, but why don't you go ahead and see what you can do with that userland stuff? And so we would go to Usenix conferences, and we would have these BOFs, birds of a feather, and Keith would get up and say, here's a list of all the programs we need. Write a version from scratch and send it in and get your name in lights, And the easy stuff like CAT came in, and eventually LS, and so on and so forth. But when things like GROF came in, we're like, oops, this may actually happen. And so Keith came in and said, oh, how's that going, guys, on the kernel? And I look at Mike, and Mike looks at me, and it's like, we can't go to Usenix and ask people to rewrite the kernel. But Keith came up with this idea there's no problem he can't solve given 10 minutes to think about it. So what we did is we took 32V, which was essentially version 7 that had been ported roughly to the VAX, and we ran it through a beautifier to put it in sort of a canonical form, and then built a database, a line, for each line, as an entry. And then we took the BSD kernel and we ran it through the same beautifier, and then we went line by line by line through every file of the kernel and looked it up to see if it appeared in 32V. And of course, you know, a brace on a line by itself, all that kind of stuff's going to pop out. But if you get like 3 or 4 lines of code that all matched, it's like, oh, we know where that came from. But you know, there's easy things to deal with. So for example, the thing that looked up, you know, you do get PID and it needs to look through and, you know, find that entry. Well, the original version 5 or 6 of Unix, basically the process table was a static 16-entry table. So it was for I equals 0, I less than 16, you know, step through the table. Well, it had gotten a little bigger, but it was still the same otherwise code. And we're like, you know, that's a couple hundred in size these days. You know, I bet if we did that with a hash lookup, it'd go a lot quicker. So we got rid of the linear search and did a hash lookup, and that code didn't look anything like AT&T. So, you know, we just did an improvement. We improved away from the problem. So we did that, blah, 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 blah. And pretty soon we had, you know, all but 6 files that were, you know, absolutely clean. And you know, it's like, well, we could do those last 6 files, but you know, if we release a whole kernel, that's going to look kind of bad. And so we'll just say, well, it's a partial kernel and you know, utilities and so on. That came out as network release 2. And there's a long, interesting story there, but I'm not going to do that one. But the upshot was that BSDI got started, which was a company that was commercially supporting this free distribution. And they did a few things that kind of caught the attention of AT&T. Like their phone number was 1-800-IT'S-UNIX. And their ads ran things like 99% cheaper than the Unix from AT&T. And you know, they didn't like that. So a lawsuit happened. And so this shirt came out. Is the things starting to heat up with, you know, may the source be with you, you know, to promote the free software. Well, whoops. The lawsuit came into full tilt, and so I had a couple more images done to try and, you know, create shirts to promote, you know, stir up trouble. So this is one of the demon, and he's slam dunking the Death Star. So I don't know if you remember, the Death Star is kind of the AT&T logo, or it was at that time. And so here he's slam dunking it. And the caption on this was net to USL 0. And then the next shirt was this one. He's standing on top of the world. He skewered the Death Star, which is kind of deflated on his trident. And the demon is wearing my Birkenstocks. And this one, I was able to find one of the shirts. So here we are with Free the Berkeley 4.4. And this, again, was a very popular shirt. I probably sold about 1,000 of those shirts. And you can see C. Peel just behind the shoe there, who's the artist, because I believe that the artist's name should remain on the art. Okay, so the BSD daemon ended up being used by a lot of the later organizations that you know, started up BSD. So there's FreeBSD and NetBSD, and before too long, OpenBSD. So this was one of the early NetBSD logos. This was one of the early OpenBSD logos. Even the FreeBSD Foundation had the daemon in a 3-piece suit. Now, of course, all of these organizations today use other logos because the daemon in certain environments is still not viewed very favorably. And so he's been kind of relegated to history at this point, but we still keep fond memories. I also came up with some of the other images that were used. This was, he was marketing, and this was sort of the image, and what he's whacking, there were a huge number of things. I mean, you know, there were some inappropriate things, like he was whacking a penguin, but there were other ones where he was, you know, whacking MS-DOS, et cetera.
Is this the first appearance of the green shoes?
yeah, so the green shoes somehow got done when it got off into the spin-off from Walnut Creek people. I don't, how that happened, I don't know. But you see green much more often now than you see the original red. But you notice that's the only clothing any of the demons are ever wearing. Just saying. Okay, this is one that I really like, the power to serve. And the BSD with the documentation, the fact that the BSD actually has like good documentation, which back in those days, I mean, you talk about Linux not being up to speed with documentation. In those days, they didn't have it. The code was the documentation as far as they were concerned. Then there was a thing called the FreeBSD News, which was a online publication. So this is D-Mon, reading through his Demon News. And then, of course, when they were getting ready to do the new 4.0 release, there he is driving a truck to carry him around. So I thought just, for historic reasons, it's kind of amusing to see the copyright assignment. So this is the letter that got written essentially from me to John Lasseter saying, these 3 pictures that you've done for me and that they're works for hire and blah, blah, blah. And so, signed by me and more interestingly, signed by John Lasseter. So it's always kind of cool to have, I have a piece of paper signed by John Lasseter. But then the real point is you then turn this into the Copyright Office. And so, I now legally have a copyright. Now, owning the copyright and actually being able to enforce the copyright turned out to be 2 rather different things. And I have been remarkably unsuccessful in many cases. There's one company in the UK that has it on vending machines for condoms. And it just pisses me off. And I actually, someone in the UK got a lawyer to look into what it would take to get them to take it out. And it was going to cost about $10,000, and that was back when $10,000 is worth a lot more than it is today. And no guarantee that, that would necessarily finish the case. And so I'm just like, fine, whatever. But whenever I get notification, I send something, and mostly they just stop using it. Occasionally they don't, but at least they know that somebody has a copyright and they're not supposed to be doing it. Just the back of the copyright there. Okay, so I'm also now going to take the opportunity, since I have 10 more minutes, to talk about 2 other things. The first one is you may notice that every 7 years we do a new edition of the textbook. And you may also notice that it has been 10 years since the most recent textbook came out. And so actually a couple years ago, we went back to Pearson Education, who were the people that currently own it. It started with Addison Wesley, and they got sold and sold and sold. Anyway, Pearson Education has it. And Pearson Education, I mentioned also that first one sold 50,000 copies. The second one sold 25,000 copies. The third one sold about 10,000 copies. And the most recent one has sold maybe 6,000 or 7,000 copies. So people just don't buy textbooks. They just grab them online for free, because inevitably it gets put online, and that's that. So it's not very remunerative, shall we say, to write a textbook anymore. That being said, we still feel like it's an important thing to do. And so we went to Pearson and said, all right, we're gung-ho. We're ready to write the next edition. And they're like, oh, well, we're kind of getting out of the textbook thing. And, we're not really sure what we're going to do here. But go ahead and write it. We'll see how maybe in a couple of years we'll feel better about it. And it's like, right. So we said, OK, fine. Will you? They hold the copyright. I mean, we signed the copyright over to them because they do the publishing. We said, will you sign the copyright back to us? And they were like, oh, well, yeah, I guess we could do that. But saying they're going to do it and actually getting it done turns out to be 2 different things. So it went back and forth and back and forth. It was like a tennis game where like no one's ever going to finish the job. But we did finally, just a few months ago, get a signed thing from Pearson saying, here it is, we're returning the copyright to you. And you have the right to use it. The only requirement is that you have to, in the front, say, previously published by Pearson Education. That's it. Fine. And they'll stop selling the current edition whenever we say we're going to release the new one. Okay, well, then the next question is, so, okay, they're not going to publish it. Who is going to publish it? And the two obvious ones were O'Reilly and No Starch Press. And O'Reilly's stuff, I mean, they haven't been doing a lot of technical book publishing. I mean, they still publish books, but they do a lot of other things. Whereas No Starch Press, they still have their nose to the grindstone and they want to do books. So I talked to them first, and they were like, yes, we want that. Please do sign up to do that. Okay, so great. We got the copyright, we got the publisher. Now this is a mere matter of writing. Well, you may remember from the previous book that there are 3 authors. There is myself, George Neville Neal, and Robert Watson. Robert Watson wrote Chapter 5, Security. George wrote the 3 networking chapters. I wrote pretty much everything else. Okay, I am now in my 70s, and I don't have quite the mental capacity that I once had. And furthermore, I sort of have this goal, like I said earlier, I didn't want to be Linus Torvalds. Well, I don't also want to be the person that this book ends if I die. So I decided to say, I think it's time to move forward. And so we're expanding the set of authors. I'm going to be responsible for the preface, the history, and okay, the fast file system. And that's it, other than cat herding. Okay, George's going to still do the networking. Robert's still going to do security. But notice we have John Baldwin, who's doing 4 and 5, kernel services, process management, and we're adding a new chapter on virtualization. That was just a section in the previous book. We're expanding that to a whole chapter because that's obviously a big deal. And so John signed up to do those. I tagged Warner. He's going to do the 7 and 8, which is the I/O system and devices, which, compared to me, Warner is just like he knows it all. So, and system startup. That's always been like the orphan chapter because nobody that ever was writing the book, including myself, really knew much about it. And so it's a really lame chapter and always has been. Warner knows a lot about system startup, so I'm expecting that chapter to be pretty beefy. And I've tagged Mark Johnson to do memory management because that's a chapter that's always been a struggle for me, but I've managed to keep doing it because I basically have Alan Cox's ear to help. I did the original ZFS with a lot of help from the original ZFS developers, but Alan Jude, of course, is just way on top of that, so he's signed up to do that. And who else should do network file systems but, of course, Rick Macklem, who's been doing a lot of that. So there's going to be a lot of cat herding going on, but I feel confident about that. And there's a set of people that are going to be able to carry this book forward in the future. So that's another checkbox that I have here. Now you're probably wondering when it is you're going to be able to buy this book. Well, it turns out that we've always done it in GROF. And the original one was done in that because that was the best thing that was available at the time. We have a macro package that jumps through hoops. I mean, if you look at it, the pages are balanced, and there's the hyphenation is dealt with, and all of that is done by GROF. But what it means is that in the past, I've had to do all of that formatting and making sure it's all laid out exactly right. We just give a PDF to the publisher, and boom, they do it. Well, these days, the kids don't use GROF. And remember, I'm trying to get myself out of the loop. And the other thing is that No Starch Press, all of their stuff is set up with LaTeX. So we're in the midst of converting from GROF to LaTeX. In fact, we had a meeting last night about it. And this turns out to be, I thought that was going to be like, a month process. And we're already on about month 4 now. And I was going to say 2/3 of the way there, but it might be a little overly optimistic. But we're getting to the point where we can kind of start to see the light at the end of the tunnel. I mean, to start off, I just wrote an awk script, which took me 6 weeks to write, to just go over and sort of massively change things. And I thought, all right, the hard work is done. No, maybe 40% was done. Anyway, so we're doing that. A lot of these authors, I've just told them, you know, don't start editing until we at least have something where we're in LaTeX, so that you'll be editing the actual LaTeX. The other benefit, of course, is that once we get this done, then No Starch Press has all the people in-house, so they can do the copy editing, they can do the typesetting, and that's also off my plate. So it's painful, but you know, going forward, all these people, you know, they had to do LaTeX for their high school, you know, papers, and they've been using it ever since. So they understand how LaTeX works, which is good because I sure don't. But John's been teaching me. I'm slow but trainable. Okay, so that was that. I have one more little thing to show off today, and that is I got a custom puzzle made by Liberty Puzzles. They are in Boulder, Colorado, and they bake these puzzles which are laser cut. So this is a 478-piece puzzle. I've brought the upper right-hand corner. So the demon that's in the upper right-hand corner, it's 85 pieces here. So I'm going to just lay this out on the table if you want to come down and see what they look like, or you know, in about 20 minutes you can put this puzzle, this piece of the puzzle together, because it's just one little part. The other thing is, of course, I got it, and so I did a YouTube video of how to assemble the puzzle in 5 minutes. And it was basically, I just put a table down with a camera down, and Eric and I just spent about 6 or 7 hours doing the puzzle, and the camera was just continuously running. And then I just edited it down, so the only part, anytime one of us puts a piece in, that little bit got clipped out, you know, and then while we contemplate for the next minute what to do next, that's all cut out. And then after you've done that, then you speed it up to 20x, and it only takes 5 minutes and it's done. Okay, so at that point, or at this point, I am ready to take any questions for the next 5 minutes. Anyone got a question? Sure.
So I agreed that the variant looked like a sperm, but before it represented a sperm, what did the glowing orb represent, or was it just an artistic flourish of lasers?
It was an artistic flourish, but it was supposed to be a light source. The whole thing in when you're doing well, animations or even pictures is you always have a light source, and then you know how you distribute that light is important. So it was you know, a sun or a moon or something, and the whole point is you see this shadow that's out behind him, and so the reason it was there was because he wanted a light source, an obvious light source that would allow him to draw the shadow. We later chose to, you know, well, that's up there, so we'll put Unix in it. That, of course, was highly contentious. AT&T had an absolute cow about that, and so you'll see later that it gets wiped out. I mean, and then FreeBSD didn't really fit in there because it was too long. So Unix is, you know, nice and it fits in a round object, but so the glowing orb has just been a glowing orb. And then, of course, the sperm cell was just because he was chasing it. And of course, you know, you have to have the streaming out behind, so you know. I mean, how do you know it's moving if you don't see the stream coming out behind it?
So if I remember correctly, at some point, Wasabi Systems had some swag that involved a green version of the Beastie with like a Japanese headscarf or something like that. Did you ever get a copy or were aware of that?
I was definitely aware of it, and I almost certainly got some piece of that swag. Although when I was going through my T-shirts, I don't recall coming across it. But you know, I had to put that whole talk together in about 3 days' time, and I had these 5 boxes of photos, and about maybe 40 large boxes of T-shirts to go through, and so a lot of it was like. And so I didn't really look at every single shirt. You know, they're folded up, so you just see like a little piece of it. And It's like, no, no, no. Oh, that might be interesting. Throw it over here, etc. It was actually good because we live in a small house, and my T-shirt collection was beginning to encroach on living areas. And so part of it was that I packed the back of our Prius as full as I could with boxes of T-shirts, and I actually took them down to the Developers Summit. And so they were, all stretched out across the front. And I, picked up some examples. But at the end of it, I said, all these over here is just swag that I got. If you want it, it's yours. And these over here are the ones that I've previously sold, so that you had to pay for those. And when I basically said, and you can, the whole room just descended on it. And it was like locusts. You could just sort of see the piles going down and down and down. So I would say I probably about 2/3 of the shirts, I brought maybe 200 shirts. And I went home with like a partially full box of one set of shirts. So, and I also got $800 for selling shirts. So, it worked out.
I just had a quick comment. I used to work at Wasabi Systems, so if you want some of that swag, I can get it to you.
Huh.
Right. And your name is? Ian. His name is Ian.
You better be careful. If they're anything like what people that came to my talk, you're going to be swamped. Okay. Anything else? All right. Thank you for coming. Come down and see the puzzle.